relevant research area. We are honored to have him with us today. On behalf of everyone present, I extend a warm welcome to Dr. Kalai Priyan and invite him to deliver his valuable session. Now, I request Dr. Kalai Priyan to kindly take over the session. Please, sir.
Thank you, ma'am.
Yes, thank you, sir.
Am I audible, ma'am?
Yes, sir, you are audible, sir.
Is it visible, ma'am?
Yeah, screen is visible, sir. Yes.
More experience
So, just a minute. So, good morning, all. Myself, Dr. Kalai Priyan, I'm working as an associate professor in School of Computer Science and Engineering, Federated Institute of Technology, Chennai. So, today we will be discussing on the topic privacy preserving techniques in federated learning. So, the main agenda of the start of this topic will continue in the four phases. Okay, actually, before that, I would like to say that. So actually, we are supposed to concentrate on privacy preserving techniques in federated learning in so precisely. So, but the thing is, so since it is shifted to the second day, I'll give you the overview of the federated learning and what are the techniques that are there, and then we will move on to the privacy. What is the need of this privacy preserving technique, and then we will move on to. So let me start the session. We will be discussing, as I said, we will be discussing it in four ways. What the agendas are. First, what is the privacy crisis? That is what is the need of being in a privacy way? So what are the way like how to secure it? And the next one goes with where it started. Okay, the federated learning. And why it is not, the federated learning has some privacy level, but why it is not so perfect. And what are the other things? That's where it comes with privacy preserving techniques in federated learning. Okay, so let us start with the case study. Okay, what is the need of this privacy? Okay, so the first thing is there are many issues that pertaining around. So let me focus on these two case studies. The first one is Samsung proprietary code leak. Okay, actually it has happened in 2023. Okay. So what happens there is there are 3 Samsung engineers who are working in I think in semiconductor industry. So in that semiconductor, the embedded code, okay, what they have done is they have for the sake of clearing the errors in the code. Okay, the one 2 guys, I think 2 guys has used the ChatGPT to optimize the code as well as to fix the errors. The third person actually used the ChatGPT to summarize the meeting. Okay, so this is what they have done. After that, what happened is all those things are being trained using their data itself. The ChatGPT got trained, and then it has so on some other query they have been exposed. Okay, so they have some loss on it. And then the next one is small book exposure. Actually, what is a small book is? It is a platform where the AI agents will interact and or like they will post the code and then they will post some comments and then the other AI agent will. So all the things are conversated by among AI agents. So what happens there is, to be so precise, there are approximately 1.5 million, as it is mentioned here, API authenticated tokens, which consists of 35,000 emails of where the humans are the owners. So based on the AI agentic queries, the other agent, the agent of AI has been delivered all these informations, and you can see the references over there. Okay, so these are the two things that is primarily I would like to discuss, and then the third one is, and the few are there, not third one, the few are there. So goes with membership inference, querying a model to see if the specific data was in the training set. So how do we extract this information from the agent is, like for example, I'll give a chest image and then check for the uh, what do we call diagnosis. So in that, for example, if it gives some information about the diagnosis, something yes or no or maybe or whatever. Okay, I can ask this chat GPT or the LLMs that using which data has been you have been trained so that you are so powerful. Like these queries, they can be made and then it can be extracted even. And if it is the agent, so if it is human in this way, if it is the A itself gives the query, agent A gives the query and then get back. So it will have one other trials, then it will fetch the information. Or for example, one more query I could. One second. Am I audible now?
Yes, sir. Audible, sir. Yes, sir.
So is my voice clear or still some noise?
Now it's clear, sir.
Hmm?
Now it's clear.
Sir, you can continue, sir.
So the next thing is goes with as I was saying, for example, earlier versions of ChatGPT, any LLMs. So if we ask them how to make guns or something, okay, how to prevent those information. So how do I find that whether this is the make of gun or in that way? So reverse psychology gets the sensitive information. Obviously, in straight way, it will not answer. But in reverse psychology, it answers in the earlier versions. Okay. So all these are comes under the privacy concerns with respect to I need some information to be handled by the LLM, but what it is happening is the LLM on the other side, it gets trained using our information itself and then leaks the data. So it gets trained with our information. So when someone else have some queries about it, it will give you more, it will give them the answer in a more clear way. Okay, that's what it is happening. And the other things are the prompt leakage. So where the users pay sensitive data into check. So that's what happened in personal identity information with respect to Samsung. And then model poisoning, malicious data is being introduced during the tuning phase. So to enhance the LLMs, so we need to tune it. So when tuning it, if there exists the malicious data, so it will get tuned with that also. Okay, and then AI-driven phishing. So there are many other cases so which we can see here. And all these things, okay, when these many things are there, okay, why do we actually go for this AI systems. So that also made us know. So when these many issues, the privacy issues are existing, so then why do we go on? That's the next point. So actually the thing is, first we will see why do we rely on that, and then we will see why this privacy matters. So the AI systems actually relies really on this data. So for the reason to give better predictions. For example, healthcare records where the diagnosis becomes very powerful in the other cases. And then banking transaction to extract the pattern. And then personal communications, which we don't rely on much. And then locations history, biometric information, so on. When they with all these information, what it becomes, the data becomes huge. When the data, only when the data becomes huge, then we will get better model, better accuracy, or the prediction value will be with better values. So we can think of these in like for recommendation systems, healthcare diagnosis, fraud detection, these informations. To predict these informations, we need a better version of model which gets trained by many of the data. So many in the sense it's of TBs of data. So when these two goes bad, so more data will give us better models. Okay. But the problem is here it comes with privacy risk. So what is this privacy risk is? Imagine if you are sharing your medical reports or banking patterns, and then you come to know that it has become publicly exposed. In that case, what do you do? So for example, if you are diagnosed with some X or Y, what do you call disease? Okay, X or Y disease, if it is so. In that case, how do we so for the sake of to get more diagnosis or to get better predictions or something like that, you are sharing your data in some versions of alarm. And then once after some time, okay, if you are being shown somewhere, okay, these persons are diagnosed with this X and Y disease. Okay, how will you react? Okay, whom to blame? These are all the problems with this AI systems, modern AI system, where the privacy has become a prime concern, right? And now, so these stakes let us understand that privacy is not optional; it is the need of the hour. Okay, and now, so let us see how this machine learning, so centralized LLMs or something like that, okay, gets these privacy risks. Okay. First thing is, in the traditional AI workflow, the user will generate the data. You can see it here. Okay. These are so for example, some users or some hospitals. Okay. So they share their data, will store in the data will be uploaded to the central server. And then centralized model will get trained. Okay. And then the model will be deployed in an LLM, and then it will give better predictions on the other side. Okay. So here comes with the risks that are listed here. Okay, I'll discuss exactly one and the others we will go. Centralized AI creates actually the data concentration problem. One compromised server can expose millions of users, correct? And then it will mention that organizations themselves. Okay, so what if the organizations themselves are selling the data or misusing the data? Okay, this is what goes with data misuse. Okay. And all the others are single point of failure. So that we know. So for that reason, we have found to decentralized storage and all the other things. But this privacy risk, how do we address? Okay, that's the prime concern. So actually, the thing is, only hackers will not do this privacy breakage. So the excessive centralization also will lead to the expose of information where I need to, so if I want some, okay, 1,000 rupees, I will hack, okay, if I want some 10 lakh rupees, I'll hack 2 to 3 accounts. What if I hack a bank? I will get more than. So, okay, that's the prime concern. And now, so in this stake, what kind of data we are supposed to protect? Okay, that comes the next question. And in the domain like healthcare, medical reports, scans, diagnosis, and in banking. So as you see here, okay, so these are the places that where the sensitive information lies inside. So we so precise. One step I will take that government citizenship identity information. Okay, like for example, in our case, this other. Okay, important observation AI models may indirectly memorize this sensitive information. That's the next. So let's come back to that government on Aadhaar cards. But what if we are exposed to Aadhaar? We know that the Aadhaar card is exposed to Aadhaar card is being exposed in some other places. So let us not dig into that. In the Aadhaar card, we are integrated with PAN number where we will get to know all the information about our uh, income. Okay, and then all the other stuff. So banking information, how many accounts do we have, all the stuff. What if that gets exposed? We do have the later on period comes with masked other ID and all the other stuff. Okay, let us not dig into that. We will see what kind of data are we supposed to protect. Okay, so now we know these are the things that we are supposed to protect. Now, this you can see this tagline. So actually, I have mentioned it for the purpose. Can we train this powerful AI models without directly sharing raw data? Okay, now sharing the raw data. So as in the earlier screen, you can see that sharing the raw data will lead to some issues. Okay. What if we can train it without sharing the raw data? Okay. Let us pause this question for now, and then we will see one more set about this, and then we will get into the question. Okay. What are the other privacy regulations available across sets? Okay, that we will see. In global privacy regulations, so they have regulations to protect this sensitive information to some extent based on the need of the country. Okay. As for that, now in this set, across the world, government organizations or the governments have realized that user data cannot be collected and used without proper protection. It should not be collected and used without proper protection. Because of this, several strong privacy regulations have been emerging globally. Okay. With this, the first shot goes with GDPR, General Data Protection Regulation, which is introduced in Europe, and based on the country aspects, they will follow it. Okay. In this GDPR, it strictly controls how organizations should collect, store, process, how to share this personal information to other forums. Okay, all the sites. And these companies that are violating this GDPR will face a massive penalty, actually. Okay. In the next goes with HIPAA. So, which it is in United States, actually, which protects the patient medical information. So, the first one goes with all the privacy information. Second one goes with, especially for healthcare. So, in the healthcare, it is in the US actually, which protects the patient medical information and ensures that health records are securely handled. For example, if it is being trained or if it is being used for some other purpose diagnosis, it is very clearly that it is securely handled. Okay. In India also, we do have DPDP Act, okay, which is Digital Personal Data Protection, which focuses on the user consent. So without the user's consent, you are not supposed to use it. And then the responsible data processing and privacy rights. Okay. In all these, so one more is there. You can see. Okay. In all these things, what are the common across all these regulations are? They all emphasize one important principle. Users should have control over their personal data. Okay. So if I want to share my data, I have to be very concerned with whom I'm sharing or what. Okay. Now this creates a major challenge for traditionally. So actually, because of these, what do we call it? Actually, because of these regulations, training the AI systems in the traditional way becomes more challenging. Okay. Because in conventional machine learning, usually it depends on collection of massive amounts of data into the centralized server, and which way where it will get trained that one model, and then it will share the further predictions in all the other cases. Okay. So in this case, Now we will come back to the question. Can we still build a powerful system without directly collecting user data? Right? Now the answer for this question is privacy preserving machine learning approaches can be used. Privacy preserving means no matter what, I'll share my data. Okay, I won't share my data. In that case, how do you train? That comes the question. Okay. So with this note, right, let us get to the federated learning. Okay, so this is the prime node for federated learning. Okay. In this phase, what we will discuss is we will get into what is the concept of federated learning, then how do we handle this privacy concern in federated learning. Okay, then we will go to the next level of what are the issues with even with the federated learning. Okay, the first one. Right. So let us discuss few about what is this federated learning. Actually, I hope few people might know this, right? The federated learning, instead of sharing the data from the server, from the user to the central server, and then gets the train a singular model, okay, with a massive data. What this federated learning concept is, it will share the model itself. Okay, it will share the model to the user. Okay, a very good example I do have. Okay, I'll show you. And now in this model, I'll use my local data to train. These models will get trained by the local data, which means, for example, if in my phone I do have some information that are to be that can be useful for training, but I don't want to share. So what do I do is I will query for, or they will share me the model where I will train the model and then share the only the weights as well as or the parameters. So the parameters only will be shared, not the entire stuff like my data. Okay, instead of giving my data to a single central server, I'm sharing it. What do? Is I will get the model, I will use my data to train this model and then share the parameters of it. Okay, where the parameters will only the numbers will be shared here. The parameter values of this model will be shared. Likewise, all the others will be shared. No? So when all these things gets shared, what the central model will do is it will use all these weights as well as parameters to get trained. Okay, right? This is what happens in federated learning. So actually, it is a massive move in terms of what do we call it? From traditional machine learning models. This one goes with a massive move because I don't want to. I have nowhere shared my data. I have shared only the model parameter. So which means the data stays in my system as such. Okay. This brings actually what the tagline that we can say is it brings the model to the data. Okay, not the data to the model, right? Then so the key characteristics includes decentralized training, and then this improves actually the privacy to the maximum, not a maximum extent, to a greater extent. No? Right. So the previous thing we were discussing some case studies now. So that Samsung has been exposed with the semiconductor set. So how if there exists federated learning from, okay, what would be the case? In the case if considering that Samsung case, okay, so where they have used the three employees, where two has been used those were using those code to LLMs to fix their code, and the third one summarized. Okay. If there exists the federated learning framework, okay, what it could be doing is they would have the internal coding assistants by themselves, which are the engineers. Source code would never leave the Samsung local source. Correct? Okay. And this mechanism held will be so what it model is considering this is decentralized. Okay. Instead of sharing the piece of code to the server and then getting it. Okay, what if there exists a federated learning framework there? Okay, so I will download the LLM locally. Okay. I will get to know my queries answers for it. And then once the job is done, only the model parameters will be shared. So where both the sides, it will get to, I mean, both the sides, it will be beneficial. It is like a win-win model, right? And now, so actually, why did we need this federated learning? It goes with the challenges in the traditional machine learning, where this federated learning addresses. Decentralized, for example, in the where this in this studies, the challenges in this existing traditional ML goes with centralized data storage, and then regulatory restrictions. Because of that, I cannot share all the sensitive information as per the restrictions. And then communication gets high cost, and then the ownership of data that matters, and then the privacy awareness should be. So in this challenges in federated learning, it addresses this data minimization where I don't want to share my data, and then reduce the privacy exposure of the cases, and then distributed intelligence as well as edge-based learning, edge device-based learning. I don't want to share my data where the model will get enclosed with me, and then I will train the model, and then I will share only the parameters. Okay. Then goes for how this federated learning actually goes with. So what do we do first is the centralized server will share the global model initialized at the server. So this will be the global model that is initialized at the server. Okay. Then what do we do is it will be shared to each and every user where they will get trained with the sets and then they will update. So like for example, here you can see, I will train my, I will receive this information of the model, then I will use it for training, and then here the trained model along with the device exists, and then I will share only the model parameters, not the actual data, and then where the centralized server will collect it, and then it will be used for with a level of secure aggregation. So here also one other catch. So this we will discuss in the next. So which means the raw data never leaves the local device. Okay. And now, so as I said here it goes with secure aggregation. Before that, we will see what is this aggregation refers to. Okay. We do have only the model parameters, correct? Okay, we do have only the model parameters. We don't have the model. Okay. For example, if the persons, like for example, here I guess. In this, for example, some 100 users are, I mean 100, what do you call, 100 tuples are there, or to be so precise, 100 records are there. 100 patient records. Here in this, the second one, it goes with 1 lakh records. Okay. Right? So now in this aggregation method, what if I take the average of all? Okay. It is not in a like of equality. But what it happens is total samples and then client model weights as well as the client data sets. Based on these three, okay, I will do the aggregation and then I will use those parameter values as to train my to train the center or to fix it in the central node. Okay. So which refers each client trains locally and then the local model weights are generated and then server computes weighted average. Like for example, after sharing this model updates, centralized server will use in terms of federated averaging, it uses three sets. So one is the client model weights, W of K, and then the client data size, which is N of K, and then the total samples. On all these three sets, it will collect all the values and then it will have the federated averaging concept to feed it into the actual model. So there the model will not get trained with this. It will be put onto the model. Okay. There are different types of federated learning methods, right? So I will take one example and then I will we will take one example and then we will disclose all the things about it. Okay. So the first one I'll take with horizontal federated learning. Okay. Where the same features but different uses are there. Okay. In vertical federated learning, different features will be used, will be there among the same users. Okay, like for example, weight, right? So in the first case, horizontal. So I will take this horizontal federated learning and we will see one thing. The case study is Google Gboard. Or what do we call it as? This so one among the keypad. So like for example, here it is, right? So in this, there exists one feature called as Google Keyboard. Okay, Gboard, which we call this. So what is the model is? It provides the next word prediction. I don't want to type any. So as well as it will go for auto correction and then personalized suggestions from based on my typing experience, it will suggest the next step. For example, if I'm using more frequently, how are you in the sense like how capital R or as well as capital E. Okay. This is the pattern that I use. Okay. What it does is it will suggest me the next how after how it will suggest me R, not A or B. Okay, if that is my pattern. And then emoji recommendations, these are all common. Okay. This is what the features of Google's AI-based mobile keyboard. Now the next question is how it gets trained. Am I sharing my personal information? That comes the next level. First, that's my pattern. How are you? That's how, but it suggests how it is possible. Right? That comes the next question. The privacy problem with the traditional learning would require actually uploading the user's typing data in prior. Okay, not in Google Gboard. In prior, if this has to be achieved. If this has to be achieved. So what are the things that we have to do is we have to upload our typing patterns, store these personal conversations in a central learning, and then goes for the training of AI models on this sensitive text. Okay, it may be sensitive, right? In federated learning solution, which is used by Google Gboard, what it does is instead of sending the typed message to Google, what actually happens is the model is sent to the mobile device. Actually, in Google Gboard, this is what happens. This is what happens. Okay. The model, the federated learning, as per the federated learning concept, the model gets into our system. Okay. Then it will be trained by the use of our own personal data in the phone itself. Okay. Only the model updates are being shared where the server aggregates it and updates for the millions of users. Now, okay, now you will get the overall picture of how would it be achieved. Okay, actually in Google Gboard, this is what the federated learning concept is being imposed and it is what is in global. Okay. This raw keyboard data never leaves the uses phone action. Okay. The benefits that we can achieve here is it provides privacy, and then personalized typing experience, large scale collaborative learning, or a reduced sensitive data collection, all these cases. Right. The final note on this is millions of users collaboratively improve the model without sharing their personal content. Right? This is what we get. Fine. So do we have any queries on till this? In any cases?
Dear participants, do you have any queries? If you have any queries, please raise your queries. Anyone having any queries? Yes.
So
Yes, yes, I will continue. Sir.
yes. So if you have any queries, then you can
Or otherwise,
please
share
do.
your queries or post your queries and chat box.
Yeah, that would
Or
be
note it down, or at the end of the presentation also we can clarify our queries.
okay. That would be
Yeah, thank you, sir.
thank you. The next one goes with out of these three types of federated learning, we disclosed one horizontal federated. Okay. The other two you can get very well exposed in the further sessions, right? The next one goes with the applications of this federated learning. Okay, so as we know that, so when this comes to the picture, then what do we think is actually our data has been never been exposed, correct? So we can use it for, in healthcare, we can use it for disease prediction by sharing our own body scan or whatever. Okay, where the medical imaging analysis and then collaborative hospital AI, and in finance also for fraud detection, I can share my pattern of expenses where if there is a sudden boom from an unauthorized account, then it could be marked as fraud detection. And then credit scoring, to be so precise, in credit scoring, so CIBIL score, as we in India, we have CIBIL score. Okay, for those and all, if we share our own information, if it is shared, then the CIBIL score will be much more effective. Unfortunately, we cannot make it. Still, it is in infertile stage of that. Okay. And then goes with smartphones, human transportation, cybersecurity, and all the other cases. So these are all the federated learning where, okay, these are all the concepts where the federated learning will be the prime case, right? Without these, it will be yet another traditional machine learning model where we do not have any privacy control over our data, right? Then. So all these has been achieved without sharing the data and storing it in a central level. Okay. In earlier stages, what is the cases? We do have this, we have dismantled this actually centralized data collection, but for the reason single point of failure, correct? So that is what we call it as decentralized data storage and all the other stuff. Like database management systems we would have studied. All those cases, right? This has been, the centralized data collection has been already avoided. But what happens is there will be multiple records and multiple cases records, and then it will be used for, if there is a single node of failure, then it will be fetched from other cases. Okay, that's what it is. But what do we mean now here is, if centralized data has been collected for the purpose of sharing, okay, in that case, what do we do? Right? In the benefits of this federated learning goes with the privacy advantages. You can see that raw data remains in the local system, and then the centralized exposure has been highly reduced, as well as greater compliance with regulations. So the next concern comes with regulations. When you impose this federated learning concept in your organization, if suppose, for example, let us take the case study of Google. Okay, only because of imposing the federated learning framework, okay, in their system, they can now achieve the better versions than the other keyboard app. Let us restrict to that one application. Okay. If it is not, then I want their data to give their personal experience. I want their data to give personalized experience. Right? If it is the case, then what would have been? Either they would have avoided upgrading their system to a user personalized experience, or in the other case, they would have not followed the regulations. In one of these two cases, it would be high risk. If it is the federated learning concept was being imposed in their framework, then now that's what the success of Google Gboard that we are meeting. Okay. In terms of technical advantages, we do have reduced bandwidth usage. For example, uh, if I have one, each user has some 100,000 data. Okay. We have to share among the set, okay, over the internet. So which will have a traffic to some extent, right? And then real-time edge learning, then the personalized local adaptation, and scalability across devices. All these are technical advantages. In terms of organizational level, data ownership is preserved. Okay, I can proudly advertise about my company. We never own your data, right? With one tagline, they can sell all their products, right? And then cross-institutional collaboration is also much better possible. Okay, for example, like sharing the information of a patient from hospital 1 to hospital 2, if they want the second opinion. For example, if they want a second opinion, they can share the data among the hospital collaborations itself, and then they can get to the other sites, right? Now, here comes the privacy concerns. Now, can this privacy still leak even when the data stays local? That's the next question, right? So for that, yes, right? The federated learning is actually not completely secure. Okay. By default, it has, the framework has the privacy by itself. But what happens in the other side is this federated learning obviously improves this privacy, right? It that's from the from the model parameters that I share. Okay, they can rebuild the data, right? What if I say this? From the model parameters that I use, right? They can predict what kind of input would made this model parameters to be invisible, right? The possible attacks are the gradient leakage attacks. The first one is gradient leakage attacks, right? What does this attack refers to is the attackers reconstruct the sensitive training data, so which I have not shared via the shared model updates. Okay, that's what we call it as gradient leakage attacks. And in terms of model inversion attack, the adversaries infer to original input data by analyzing the model outputs. So, for example, if I give the model parameter, they will fix it into the set, and then they will give the input, and then they will take this some output. Correct? From that output, I can predict what kind of input it could have been. Right? So, because the thing is, we know that machine learning is a data-driven set, okay, where the input and output are existing. And the only thing that we don't know is what is the algorithm that converted this input to the output. That's what exact machine learning comes with. That's why we do not call machine learning as an algorithm rather than it is a model, right? There is input, there is output. But what made this both correlate? How this input gives this output? That we don't know. Okay. That central part algorithm is what we do call it as machine learning models. We'll generate the algorithm, for example, in a layman's perspective. Okay. It will generate the algorithm that maps the input with the output. Okay. Now, in this private federated learning concept itself, also, we do have this model inversion attack in the way like I do have the input, original input data. I don't have the input original data, but I do have the algorithm as well as the output. Okay. With this, I can predict what kind of input, right? Then the membership inference attack. The third one goes with membership inference attack. In this, the attackers determine whether a particular user's data was part of the training data set or not. Right? So I can, like the one example that I was discussing earlier. Okay. I can query the LLM, which kind of, I cannot query the algorithm set, these kind of, or which kind of data set you have used. But I can query that whether you have used this person's information or not. Okay. It can say yes or no. It cannot expose the more data, obviously. It will not. But it can say yes or no. If it says yes, what happens? Then they know my information already, but this information they don't know. But they know that now they know that I have been a part of training. Okay, so then they will try to attack my membership inference, and then they will expose my info, right? And the fourth one goes with poisoning attacks. In this, malicious clients intentionally send manipulated updates to corrupt the model. Okay, what if the data? I have not shared my data. No. Okay, no issues. What if I pretend to be like I have the data, you give me your model, I will train it and I will send you the information. What if I hack that and then give you manipulated data? Data means the model updates. Model updates are not from the actual trained model. It is from the user's perspective itself, right? What if that costs points? All these are the further attacks of federated learning. Okay, now here comes the picture of the need of privacy preserving techniques even in this federated learning. Okay. I don't think we have time to expose all the privacy preserving techniques. So what I have done is I have taken some 3 privacy preserving techniques, and then with that we will get some depth of, right? First one goes with differential privacy. What happens is, to be in one liner, what happens is the model parameters that I'm giving, for example, if I'm the authenticated user and I have trained my model, I have trained the model that you have given with my data, and then it goes with the next level. So sharing of information, right? What if, so let us consider all these things we have already discussed. Let us consider that if I share, while sharing the model updates, what if I add some random noise generator? Okay, this noise generator is called as differential privacy. And then what do we do is we will impose some noise over the data. Okay, so now what it is being shared is the noisy update. The noisy update has been shared. Okay, and then final set goes with noisy labels, noisy update to some extent, where now you cannot expose the entire data of mine. Correct? This is one way of addressing the privacy in federated learning. Okay, what do we do is in one liner, what do we do is we will take the, while sharing the local updates, okay, I will add some error with it, or to be so precise, it is noise with it, and then we will share the information. Now, even if you try to rebuild the input data from the noisy updates, it is now becomes highly hard. It is not impossible, it is hard. Okay. And now the privacy utility trade-off goes with the trade-off between these kind of noise imposing is, if more noise are imposed, it goes to better privacy. But on the other side, if more noise are imposed, the model will get less accuracy. Actually, this differential privacy is useful in many of the things like healthcare AI, financial analytics, mobile device learning, in all these cases. Okay. Next one goes with secure aggregation. In this secure aggregation, what do we have is, so imagine it like a, okay, we have finished the voting concepts now. So let us take that example. It is a sealed ballot box, correct? All the ballot boxes are sealed. Okay. What information a personal voter has been voted, that we don't know, correct? It has been collectively grouped in a system, like for example, that ballot box. Okay. In that ballot box, some 1,000 people of my constituent has been voted. Okay. Now nobody knows who has voted for the other, right? Now on counting, but they know how much vote has been polled. Okay, that's what exactly this secure aggregation. What do we do is, instead of collecting the information from the sets individual level, okay, what do we do is, we will collect all the local updates and then we will group it together and then give it to the federated learning framework, right? In that way, to a greater extent, our data has been saved. Okay. It prevents the server from inspecting individual client updates, actually. Okay. Right. So the advantages includes confidentiality has been improvised to a greater extent, and then the information got, the leakage level of information gets very much reduced, and then the trust among the participants goes high, right? Because I know that I voted for some person, right? I know I have given the local update to some extent. Okay. And then collectively all the others has been done. And then when the server, it gets reached to the server, it is given to it in a collective manner. Now they cannot extract from which in-person information I got the update, right? Because it is already available, right? And the third one goes with homomorphic encryption. There is another level, okay, where the computation is being performed directly on the encrypted data itself. Okay, like for example, the data that I give, okay, it is not raw data, it is encrypted data. What if this is the case, right? In all these three aspects, the privacy is the prime concern. And in all these three cases, we are achieving the privacy to a greater extent, right? This is the major advantage that we can see in all these. There are many other models, but I don't think it will be good at the initial days of FT. Okay. Anyhow, in the rest of the sessions, we will be having all those things. Fine. The next one goes with, let us discuss some about 10 minutes for the research challenges in federated learning, and then we will go for the open classes, right? Students. Right. Let us discuss one by one. In terms of research challenges, the first goes with communication challenge. Okay. The very first of it is frequent client server communication. Correct? So I will give one information. The model will try for it. And then it will ask one again to train and give that information. Right. It will give some input. And then based on that, with my data, I will get it trained and then share them. Right. So this two-way communication is often happens till the model gets a global update. Okay. And this requires the high bandwidth also, right? So what if the model is huge? What if my phone cannot accommodate them? Because one of the users are phone also, right? It is not like only phone uses G keyboard, correct? Google keyboard. So let us take that example. Okay. Then in terms of data, okay, non-IID data also gets distributed, right? For personal information software. And then imbalanced local data sets. What if the person has, like I said, 100 data in one system and then 1 lakh data in one system? How do I handle this effectively? What if the data is from the heterogeneous client environments? Like one from mobile phone, one from laptop device or something. The third one goes with system challenges. What if the client drops? Okay. So I highly rely on some information that will be shared by some people. Out of those, only half of the people are shared. The other client is going wrong. What if the device has some limitations? Like for example, all our laptops, correct? Okay, but mine has 32 GB, someone has 64 GB, others has 256 GB of something. Okay, 64 GB of RAM, and some has 16 GB of RAM. What if this device has some resource limitations? How do we blame them? Not possible, no? For all this together, if I share the data model in a very low level, like for example, optimization is fine. Optimization model is fine. But if it is low weight data, then it cannot afford my huge data. If I go for high level data, that the device cannot. So these are all system level challenges. And then in security level, as I said earlier, the gradient increase for poisoning attacks. Still, there is no concern for poisoning attacks because we know that only the information we can get it from the user. But what if the data itself, the information itself manipulated? How do we cross it? And in these cases, the stronger privacy mechanisms, okay, if the stronger privacy mechanism comes with, it will have increased computational overload. Okay. And but it will also reduce the efficiency of training. And it affects the model accuracy heavily. And these are the research focus ideas. What would be, from my point of view, what would be the suggestions are the lightweight privacy preserving techniques are much well, okay, and efficient secure aggregation. Okay, like I said, in homomorphic, the data itself get trained from the encrypted level. Okay, the previous one was secure aggregation, where like a ballot box, right? What if much secure aggregation exists? Okay, and then privacy mechanisms should be adaptive from person to person, as well as the communication. Efficient communication from the federated learning is also a prime factor of this research. Then we'll go with the future of privacy preserve. Okay, the first one goes with what do we get to know in this FDP session is these emerging areas, right? One among these emerging areas is quantum safe federated learning. In what way I can impose this quantum safe, right, in the federated learning to achieve better efficiency in terms of privacy preserve. Okay. And then the next goes with, in terms of federated learning, the other goes with blockchain assisted. So like, for example, I will store my information in the blockchain and then it will get trained from there, from that place later. So where I will not disclose my sets. Okay. And then AI-driven adaptive privacy, decentralized trust level frameworks, and then edge native intelligence systems are some of the other sets. Okay. In terms of security, post-quantum cryptography is one among the better approach, so which you will see in the right in the next session. Okay. And secure decentralized aggregation also one concern of it, and then zero level trust in federated learning. So you know that is a KP. Okay. And then explainable privacy mechanisms are also another concern. And then the final set goes with industrial future, where the smart healthcare ecosystems are there, and then autonomous transportation, all the others, right? So with this, I'll have the end of my session. I would like to expose one other thing, okay, where if you're the people who are trying to impose from the federated learning concepts, okay, I will share you one. This is folder. Here, try for flower.ai. Okay, where you will have, how do we install this flower in your set? Okay, where it will have a line by line description. What is the actual cases? Here, what it will happen is it will try to simulate the framework in our system itself. Like, for example, uh, we will have a central work, and then it will generate multiple clients in our system itself. Okay, like via the command prompt, it will have more number of client sets. And then what do we do is from each side, we can give few set of training. For example, where that comes with the horizontal filtered learning, some different level of data, or small data, large set of data. All these trials are there. Okay, and it uses all those if you want homomorphic encryption in all the other sets, it also helps. So you try with that with this flower.ai, which is actually very highly useful for those who are in better learning. From this, you try to carry on. How do we impose the quantum part of it? Okay. So that's what I would like to expose to. And if you have any other queries, you can ask.
Yes, sir. Now we will open the floor for participants' queries. Dear participants, if you have any questions or clarification, please unmute yourself and raise your queries. Sir is here for clarifying your doubts. Anyone having any doubts? Dear participants, if you have any doubts, please ask. Anyone? Is anyone having any doubt? Participants? Yes, sir. Thank you so much, sir, for your highly
Thank you.
informative and insightful session, sir, on this privacy preserving techniques in federated learning. Your presentation provided us with a clear understanding of this important research area and highlighted its significance in today's evolving technological landscape. The way you explained the concepts with clarity and connected them to practical applications made this session truly engaging and valuable for all of us. Your expertise and depth knowledge in emerging technologies have greatly enriched our learning experiences. On behalf of the organizing team and all the participants, I sincerely thank you for taking the time to share your knowledge and valuable insights with us today. We are truly grateful for your presence and contribution to this FDP, sir. Thank you once again, sir, and we look forward to more such enlightening sessions from your side in future. Thank you so much, sir. Thank you so much, sir.
Thank you.
Yeah, thank you, sir. And I request all the participants to kindly submit the feedback form. We have already posted in our chat box. So please make sure that you need to maintain at least 80% of attendance. Then only you are eligible to receive the certificates. Dear participants, we have posted. Dear participants, we have already posted feedback form link in the chat box. I kindly request all the participants to submit the form. You make sure that you need to maintain at least 80% of attendance. Then only you can receive the certificate. I kindly request all the participants to submit the feedback form. Already we have posted the feedback form link in the chat box. So this session is over. After submitting your feedback form, you may kindly leave the meeting and you need to rejoin the meeting by 10:50 a.m. Okay? Because as our next session will promptly begin at 11 a.m. Dear participants, I kindly request to rejoin the meeting by 10:55 a.m. as because Our next session will promptly begin at 11 a.m. Before that, you need to submit your feedback form. We have already posted that feedback form link in chat boxes. Yes, dear participants, welcome back to the second session of today's faculty development program. I hope you found the previous session insightful and informative. We are happy to have your continued participation, and I'm sure this session will also be highly beneficial for everyone. And one more request for all the participants. At each session, we have posted a feedback form link at the end of the session. I kindly request everyone to submit the form. Please follow this one. Now, it is my privilege to introduce our esteemed resource person for this session, Dr. Rajakumar Arul, Associate Professor and Head of the Department for BTech CEC Quantum Computing at Vellore Institute of Technology, Chennai. Dr. Rajakumar Arul is a respected academic leader and researcher with expertise in quantum computing, quantum cryptography, post-quantum security, network security, and artificial intelligence. He has made notable contributions to interdisciplinary research by integrating classical and quantum computing approaches to address critical challenges in secure communications and intelligence systems. He has published several research papers in reputed journals and conferences demonstrating his strong commitment to advancing research in emerging technologies. A significant highlight of his academic leadership is his instrumental role in developing the BTech CSE specialization in quantum computing at VIT Chennai, one of the first of its kind undergraduate programs in India, designed in alignment with global technological developments and objectives of National Quantum Mission. Today, he will be delivering an insightful session on quantum cryptography and post-quantum security, a topic of immense relevance in the evolving landscape of quantum technologies. We are honored to have him with us today. On behalf of everyone present, I extend a warm welcome to Dr. Rajakumar Arul and invite him to deliver his valuable session. Now, I request Dr. Rajakumar Arul to kindly take over the session. Please, sir.
Yeah, very good morning, ma'am. Can you hear
Yes,
me?
yes, sir. We are audible, sir, and your screen is also visible. Yes.
Okay. Yeah. So let me share my screen. Second. Ma'am, can you see my screen?
Yes,
Is it?
sir. Yes,
Yes,
it's visible,
Professor.
sir. Yes, sir.
Very good morning, Professor.
Yeah, very good morning, sir. Okay, so very happy morning to everyone present here. So myself, I am Rajkumar Arul, and currently I'm associated with a School of Computer Science and Engineering at VIT. Okay, so I have made this session in a way that, okay, so I will try my best to expose you to the major pillars like quantum cryptography and post-quantum security. So I have taken an assumption while preparing this slide, so you are completely new to this paradigm, and feel free to interrupt me whenever you want. And if you have any queries, comments, suggestions, please feel free to interact with me. So with that, okay, so let's start. So what if all passwords become visible tomorrow? So the main thing, like why we need to migrate to post-quantum cryptography, or what is the necessity that I need to look for some alternates like quantum cryptography. So the main reason is, so wherever we are, so now the globe is completely connected to the internet, and all the services what we avail through internet are believed to be fully secured. And this security is being ensured with different cryptographic algorithms in place. And all these cryptographic algorithms heavily relies on hard mathematical problems. So since I believe all of us in this meeting are from pure CSE or from engineering background, so you might be knowing about the algorithms what we use in every day. And so as I said, so the cryptographic algorithms heavily relies on the hard mathematical problems, and some of its applications and use cases are predominantly on the banking systems, and then the military communication banking system, So the reason being, as we all know that today nobody is carrying cash. So all is done through only UPIs and internet banking. So all these are securely handled only with these cryptographic algorithms. Military communication, most possibly, so all the information of our military secrets must be protected. And systems like Aadhaar, and you have our own DigiLockers. Okay, so all these things are now very easy for us to use. So only reason is being the cryptographic algorithms in place. Okay. So, and also we have some of the technologies like blockchain, and healthcare records is something that is very unique, because we in Western there are many platforms where you can even have a track of what are the drugs you took even from your childhood till whatever age it may be, even in your old age. There is a system which can hold all the records, but still in India it is not completely ready as of now. But most likely that even in few years we will have that system in practice. So all these things are basically depending on the cryptographic primitives. Okay, so what if any of our password, what we believe or what you use, are visible tomorrow? Okay, so in that sense, assuming that you have an internet banking, you know about your username and you know about your password, and the password what you keep. So you might have seen some of the guidelines, like you should use an uppercase, you should use a symbol, there is no lowercase, your first name should not come, last name should not come. So all these guidelines are being provided to you. And also the length of the password, say you must have at least 8 characters, or 8 digits including numbers and symbols, or 12 digits including numbers and symbols. So all these are guidelines that is given. Okay, so the reason being why we are receiving those guidelines, the key parameter is, so how can I determine what is the key that you are using, or what is the password you are using? So literally it takes, so for every character it is again an exponential trial. Okay, so using a trial and error method, we try all the possible combinations, which in turn, if you say that I have a password of 12 digit, or most possibly, like, so it will be again converted into a binary, which will have 12 any number of bits. Okay, assuming that if it is 256 bit, you say that it is going to be a combination of 2 power 256 iterations to find its password, right? So it takes a huge amount of time from our classical computers, or the computers what we use. We coin these computers as classical computer. We have to run 2 power 256 iterations, which will provide us all the combinations of the password, and then out of which one will be the correct password, right? So when you had more combination to your password, the thing being, so for finding this combination 2 power 256 or 2 power 512, we say that it will take some amount of years to compute. Okay, so that is the reality. So now when I say, if you have a chance that you have a computer that will not take some years to provide this combination, instead hours or days to provide the combination. Okay, so that is the space where the quantum computer comes in. Okay, so I have some slides where we will discuss in detail about how a quantum computer can breach, or how a quantum computer can help us to find these passwords, right? So purely that is the main reason why across the globe, every country started investing money in quantum cryptography and post-quantum techniques. Okay, so I have some of the slides that are prepared that will expose you why it is a need of the hour. Okay, and a general declaration. So all the informations presented during the entire presentation are purely based on my experience. And I have been working in this domain for almost 8 to 9 years. So with that experience, I'm sharing what I know. So to understand the cryptography better, so let's start from the evolution of the cryptography. So it started with the ancient technique, so very old system, that is the Caesar cipher, where instead of one alphabet, we use a different alphabet. For, say, instead of A, I will say everywhere, whatever. Let us take, we have 26 alphabets. Okay, so I will say, so wherever you pick an alphabet, add a +2. Okay, so meaning the second letter from what the letter you are picking. So I will take that letter as my a cipher. Okay, so for example, every A will be replaced by +2 means B and C. Okay, so you say that every A will be replaced by C. Likewise, B will be replaced by D. So likewise, you say that. Okay, so in this context, the +2 is the key what we have, and the converted text. Okay, so I'm replacing a text and I call that text as a ciphertext. Okay, so this is the very ancient method. So at that time, there was no computing devices, or there is no high performance computing devices. So that was working fine. At that time, the communication was happening only through offline. So a person will carry the note in a sealed packet, and then he will deliver it to the different countries. So at that time, it was working. But after that, so once there was an improvement in the technology, so we started to have computing devices. So where you are supposed to send, or you can communicate with a person at different locations. There is no necessity for us to go and talk to them, right? So in that context, so we wanted a secure mean. So Caesar cipher won't work because you can easily figure out what is the key. Okay, so because you have a computational device and you can easily run through all the combinations at very easy pace. Okay, so we moved on to the classical systems, where we say DES and AES are the best example for the classical systems. So in that, you have some of the primitives where you feed in your plain text, you add some component in the name of a key. So add these two things to build your ciphertext. Okay, and the ciphertext is, again, you do some mechanisms, an inverse of what you have done earlier, and then you will get back your original plain text. This is what was the classical means was doing. Okay, and then we felt that it is also not sufficient. Okay, so we moved on to the modern strategies, where we had RSC and ECC. So even today, you can see most of our communications, what we do with WhatsApp or Meta or LinkedIn, you can see that there will be for example, you take any new number which you have not communicated earlier. So you just click on a new chat, and you can see there is a pop-up in that message in WhatsApp. You can see that all the messages what you are sending to this person is being encrypted. Okay, so that encrypted, there will be an option to see learn more or read more. So you click on that, and it will redirect you to an official page of WhatsApp, where you will get to know, so what are the algorithms that WhatsApp is using to encrypt your own messages. Okay, so all the messages what you send through WhatsApp are being encrypted, and on the other side, it is being decrypted and shared. So meaning, so nobody in the middle is supposed, or it is exposed, so nothing is there. Okay, so whatever the message you are sending to your friend, so only you and your friend can see. So that is the claim that WhatsApp is making. But so I don't want to give any comment on that, because in the international forums, we can see there are arguments where they talk about, no, I'm seeing all the ads very closely pertaining to what I'm chatting with my friend. Even you can feel that in your YouTube or something. Okay, so for example, you say that to your friend, you just send a message saying that I want a car wash showroom, or I want to go for a dinner today night. Okay, so you just send a WhatsApp message, and you just go onto YouTube, and you search for something. There will be an ad popping up, and that ad will possibly give you suggestions on the text what you sent over WhatsApp. Okay, so many feel like, okay, so WhatsApp is revealing the information. The answer is not WhatsApp is revealing the information. Instead, so your Google keyboard and the account where you are using, okay, so that reads your keystrokes. Okay, so these are some general myths what we know. Okay, so and as I said, so even this is not sufficient for us, because when there is a possible very good or sophisticated quantum computer coming into picture, all these algorithms what we use, what you say that modern or classical or any ciphering algorithm or any cryptographic algorithms what we use today, can be easily broken. Okay, so I will explain you how that is made possible, and that is the reason. So people started. Okay, so this drive is being started before a decade. Okay, so NIST has given the guidelines on what is expected, and researchers across the globe were trying their best to provide some solutions which can closely come in line with the NIST requirement. And we have some of the PQC algorithm, that is post-quantum cryptographic algorithms, being standardized. So, and at this point, I would like to clearly tell you, so quantum cryptography is completely different and post-quantum cryptography is entirely different. Okay, they are not overlapping spectrum. They are purely different spectrums. So in quantum cryptography, we use quantum mechanics principle for cryptographic algorithms, whereas the post-quantum cryptography, we don't use any of the measures from quantum computing paradigm or quantum mechanics or quantum physics. Nothing is there. The traditional machines what we use today, we use the same machines without any modifications. We want some solutions to be made in the same machines what we use, and we say that as a PQC algorithms. Okay, so only it carries the name that post-quantum, but it is not quantum dependent. We say that it is safe from quantum computer attacks. So possibly at the end of this session, so you will get to know so how these two are different pillars. And so moving further, so why current encryption algorithms or whatever the cryptographic suits or the algorithms we say, mechanisms, how they work. So basically they work on two predominant problems from mathematics. So the first one is the factorizing a large prime number. Okay, so you take RSA, so RSA or ECC, so you want some large prime number to create your asymmetric key. Okay, so asymmetric key in the sense you will use one key to lock and there will be another key to unlock. Okay, so it's not the same key. We say a symmetric scheme where you will use the same key to lock and the same key will be used for unlocking also. Okay, so here large prime number plays a vital role in RSA. So can I factorize that large prime number? No, it will take years in our computer to factorize it. So there were many factorization methods, but still you know that, okay, so when I use a large prime number, it takes years to find its factors. Okay, so that property is being used in all the places where RSA being used, right? So in RSA, the primary assumption, the first assumption what we take is take the large prime number and then use that prime number to compute all other derivatives. Okay, so similarly, the other spectrum is the discrete logarithmic problem. So anything that is raised to the power. Okay, so that we call that the discrete logarithmic power. And one very good example is all the key exchange mechanisms what we use, and predominantly the Diffie-Hellman key exchange mechanism. So these two are the predominant problems that we believe that, okay, so these problems can never be solved in a classical machine, or a classical machine can never solve these problems in the definite amount of time. Okay, so you can see there are session keys, there are you can see that, okay, so your session is being logged out because of inactivity. So all these times are like fixed based on the size of the key you are using. Okay, so that decides. Okay, so we set the benchmark saying that now within this time frame, this key cannot be identified even by a supercomputer. Okay, so all these whatever the mainframe are almost right. So in today's era, so we have almost reached the Moore's law's limitation. So we have almost reached a saturated state where we cannot scale our computation further. Okay, so that is the maximum potential that what we can unleash from a silicon chip. So we have almost reached that spectrum, and hence we declare that, okay, so this is the most powerful machines that a human can build with this architecture, and within that architecture, or by using that architecture, these algorithms can never be broken. That claim is perfectly valid and it will be valid forever. But the thing is, see, the quantum computer is completely different from what we are using right now. So quantum, so let me give you a very, very basic understanding of how a quantum computer works so that it will be very easy for you to grasp the rest of this session. So in our classical computer, we use bits. Okay, so bits in that sense, I will say, if I ask you, so what are you doing right now? Okay, so you will say, I am listening to my session. Okay, so in a classical computer, you can say that I listened to the session or I will listen the session. Okay, you can say either yes or no. So that is binary. So you say that is 1 or 0. There is no concept of saying that there is an intermediate state that what you are listening right now. Okay, so you cannot represent this state in a quantum computer, I mean, in a classical computer. But the quantum computer is a natural way of computing it. Okay, so you say that, okay, so are you listening to me? You will say yes. Okay, and have you listened to me? So possibly or probably you will say yes or no. Okay, so quantum computer works in the probabilistic principle. Okay, so the percentage of, okay, so how much you have listened, probability of listened is, okay, so 40%, probability of listened is less than, I mean, not listening is 60%. So every bit will carry both the states. Okay, so it's a probabilistic model. So that is why I said, so in a classical computer, you say there is a bit, it will have either 0 or 1. In a quantum computer, you say there is a bit, we call that as a qubit in a quantum computer, that will hold both 0 as well as 1. Okay, so in that context, we say that a probability of 1 is 50%, probability of 0 is 50%. So when there is a 50% and 50% probability, you have both the states. You will have 1 as well as you will have 0. If the probability of 1 is 100, then you will have only 1. The probability of 0 is 100, you will have only 0. And if the probability of 1 is 50 and the 0 is 50, you will have both the states. Okay, so this is the magic that the quantum computer brings in. Since it can hold both the states, see, whatever the numbers what we discussed earlier. So for example, I said 2 power 256 combinations is needed to find one 256-bit key. Okay. So in our classical computer, you will take every bit, you will use either 1 or 0 in every bit to find all the combinations. But in a classical, I mean, in a quantum computer, you have the provision that every qubit can hold both 0 as well as 1. Okay, so in that context, you say, I want to know, okay, so whether it is 0 or 1. So in one shot, you will have both 0 as well as 1. Okay, within 2 qubits, you can simulate 4 states. 4 possibilities will comes out only with 2 bits. Okay, so in one shot, you will get to know 4 possibilities. Whereas the same, if you want to do it in the classical computer, you need 4 iterations to find the 4 combinations. Okay, so that is the high potent or exponential power the quantum computer brings in. And as I said, all these algorithms are relying only on the computational hardness. So what do I mean by computational hardness? It refers to the property that, okay, so this prime number, the large prime number, cannot be factorized by a computer within this time frame. That is the computational hardness. Okay, so we use that property so that I have the confidence that, okay, so this can never be revealed or this can never be used. Okay, so this is how the system works here. So as I said, so how we decide that the quantum computing will disrupt these whatever we are using for many years? How is it even possible? Okay. So that is purely based on some of the principles that the quantum computing holds. The first thing is the qubit. So that is what I was discussing with you till now. So every qubit will hold both the states. So it is not going to be either 1 or either 0. It can be 1, it can be 0, or it can be both 0 and 1. Okay. And the superposition is the principle that supports that qubit to have all these concepts, right? I mean, to have the states. Okay. So especially there is a gate called Hadamard gate. When you apply a Hadamard gate to a qubit, it says you will have 50% of 0 and 50% of 1. Okay. So which means you will have both 0 and 1 in one bit. Okay. In one qubit. And there is a property called entanglement. Okay, so entanglement is a wonderful property that you will be surprised okay, so let me give you a sample instance so that it becomes very clear. So you say that I have two components with me. Okay, so assume that I have two bulbs with me, and these two bulbs are now assuming that they are entangled. Okay, so what I mean by entangled is, let us say that, okay, so these are colored bulbs, and now I say that these are entangled and these two bulbs are now glowing in red color. Okay, two bulbs are now glowing in red color. And what I'm going to do is I will hold one bulb with me, and the other bulb, okay, I will give it to my friend, and he is going to travel to US tonight. Okay. So after some time, he reached USA. Now his bulb will also be glowing in red color. So when I change the color of the bulb, what I have, to blue color, there is no connectivity between the bulb what I hold and the bulb what my friend is having currently. When I change the bulb what I have with me to blue color, the bulb what he is holding in USA will also change to blue color. Okay, so it's like a magic. So this property is what we call it as entanglement. Okay, so you alter you measure something on one qubit, the same is being reflected on your entangled qubit. Okay, so it is like, again, okay, so it's a deep research. People are trying how is it even possible, how this magic is happening. Okay, so that is a very interesting spectrum, and this is also one property which we use in quantum computing paradigms. Okay, and quantum parallelism. So as I said, okay, so for example, I want to figure out the 2 power 256 combinations. Okay, so in a classical computer, you will always go one by one, and even if you run parallel threads, possibly how you can achieve parallelism is like, you say that, okay, first 100 combination there will be a thread running, second 100 there will be a thread running, and 400, I mean third 100, 400. Okay, so likewise you can have a split, and then you can run threads to achieve parallelism. But in quantum computing, so by nature, okay, so you achieve this parallelism because it holds both the states. Okay, so you get a vast amount of parallelism achieved through every qubits what we use. Okay, so these are the things that really creates an interruption in the cryptographic algorithms what are in practice today. Okay, fine. So, okay, so quantum computers are fine, perfect, no problem at all. Okay, so, and they say that, okay, so these properties will disrupt these algorithms. So you can see in this slide, so two Jains. Okay, so the first on your left, who is wearing the specs, we call him as Peter Shaw, and the other one on the right is the Love Groover. Okay, so these two fellows are like, they are like a wizard. Like, so the Peter Shaw has come up with an algorithm called Shor's algorithm, so which can factorize any prime number in polynomial time. Okay, so far we believed that the computational hardness decides. Okay, so these are safe algorithms to use, but this guy has completely proven wrong that he has come up with an algorithm that can run in a quantum computer that will break the all the cryptographic algorithms what we have right. Okay, so because it can easily factorize any large prime number in polynomial time. So what do you mean by polynomial time? For example, we say that, okay, so it will definitely, the classical computer will take 30 years to find this key. Okay, so that 30 years can be reduced to 6 minutes if you have a quantum computer. Okay, so that is the realistic picture that Peter Shaw has brought us. And similarly, the other guy, so who is the Love Groover, so he came up with a search algorithm basically that purely works on the amplification of your phase shifts. Okay, so it's like, so you can easily search for the entity that what you are looking for with a phase shift in the quantum paradigm. Okay, so to give you a clear picture, so Groover algorithm works in a way like, okay, so in a quantum computer we always use complex numbers. Okay, so you are completely aware that in a complex number, Negative means it's a phase shift, right? So when I say, when I want to, okay, so I want to search for a key, okay, so a matching key in the given spectrum. So what I need to do is, see, you just convert that as a different phase. For example, instead of +5, you make it as a -5. So what happens is, see, when it is a -5, let us assume that it's a 2D plane. So something on your y-axis will be on the positive side, and something on your y-axis, a negative number will be on the bottom, right? On the quarter 4. So on the bottom, we will have that. So what happens is, see, you convert a +5 to a -5. So only the -5 is getting, I mean, it is plotted on your bottom of your x-axis, right? So when you amplify the probability, what happens is, see, negative numbers will grow and positive numbers will shrink, right? So whenever you increase the number of iterations, so your negative numbers will amplify and your positive numbers will shrink, okay? So in that context, even within very small iterations, so you can easily find out whether it is present or not, okay? So that search is being, so he brought in under the complexity of log n, okay? So that is the achievement what he has brought us. And as I said, these two are made possible only when you have a sophisticated quantum computer in practice. So theoretically, they have proved that, okay, so if there is a quantum computer of these many qubits, then these algorithms can be easily breached within this time frame. Okay, so now you may have a question. Okay, so what do you mean by a sophisticated quantum computer with a sufficient number of qubits? Okay, so now we have quantum computers, and all the quantum computers what we have are having physical qubits. Okay, so physical qubits are highly prone to error. In that sense, as I said, so there is a gate called Hadamard gate. So when you apply a Hadamard gate on a qubit, it has to provide you a superposition of 50% of 1 and 50% of 0. Okay. In reality, when you run or when you put this Hadamard gate, what will happen is, so you will get a probability of 60% or 55% of 0 and 42% of 1. Okay, so you see that there is a error. Okay? So Hadamard gate must give us 50-50, but due to its physical property, there will be a huge error. I mean, we call that as a noise in a quantum computer, and quantum computers are highly prone to noise. So error correction by itself is a big research area in a quantum computer. Let us not get into that spectrum. So what I'm trying to convey here is, so these fellows have brought in their algorithm that will work in logical qubits, meaning theoretically whatever they have said, the same theoretical version must have been in practice. Okay, theoretically we are saying that when I apply Hadamard gate, it has to be 50% and 50%. Okay, so what in reality is, it's not giving us 50% and 50%, rather there is some changes in the values. So what now the researchers are doing is, they form many number of physical qubits, and they take the average of it and they call it as a logical qubit. Okay, say I will have some physical 10 qubits, and I will combine these 10 physical qubits, and I say that I'm going to take the average value of all these 10 qubits, physical qubits, and I'm going to call that as one logical qubit. Okay, so if I am able to build a quantum computer of sophisticated numbers, then it is perfectly fine. These two will be achieved. Okay, so currently in India, so we have, till date, we don't have a big quantum computer. So when I say quantum computer, there are very many different flavors. Okay, so one can be ion trapped, the other can be photonics based, and then you have NMR based, and even you have semiconducting. Okay, so semiconductings are a bit very costlier, where you will have the diffusion refrigerator, where you must be able to clock 0 Kelvin temperature. Okay, so only in that temperature your semiconductivity will happen. Okay, so in India, so now our Indian government has sponsored, and there is a quantum computer coming up in Amravati, and also I think that is now in I mean, it's open for the public. And also now CDAC is planning to procure a quantum computer of 108 qubit, and which is going to be erected in Bangalore. Okay, so this is something that is going to happen. And as I said, so with this 108 number of qubit, they are physical qubits. Okay, so the cost of that machine will comes around 800 to 1000 crores. So with this 108 physical qubit, can I breach algorithms? No, perfectly no. Okay, so you cannot do that. So instead, but they are like a reference model. Okay, so we can run our algorithms, or we can trial our own methodologies of how we can refine and get that 50 and 50. Okay, so that error correction and everything we can do it in this 108 qubit machine, and then we can possibly scale that to any numbers what we are expecting. Okay, so as I said, so different quantum computer will have different analogy, and their working principle is completely different. What they share in common is the quantum principle. So the principles of quantum mechanics and the quantum physics are the only thing that is common among them, and all the rest of that, the architecture is different, everything is completely different. Okay, but in general, we use quantum circuits to run on these quantum computers. Okay, so this is only to realize them. Like, so to understand how things work, so we are building a quantum circuit and we are running that quantum circuit on these quantum machines or the quantum computers. So are we in sync? Can I have a quick yes or no or some reactions?
Yes, sir.
Yeah, thank you.
Yes, sir.
Thank
Yes.
you. Yeah, fine. Thank you. Okay, so going further, so we have the quantum threat timeline. So basically, what is the problem now? Okay, so the biggest problem is harvest now and decrypt later. So the conversations what we do today. So today we don't have the sophisticated quantum computer to breach any of our algorithms. Okay, so that is a clear claim that we can also believe. But the problem is, so the conversation what we do today, just don't do anything. You just store these informations. When the sufficient number of qubit quantum computer comes up, you take the stored records, run it in the quantum computer, done. Okay, so this is the biggest problem what we are facing right now. So we don't want to wait until, or we don't want to wait saying that no, logical qubits will not come in these years. Okay, so we don't want to do that. Instead, we wanted to at least streamline the algorithms what we use. Let us say, let us want to migrate to any mechanisms that is not vulnerable to a quantum computing attack. So this is the main role. And as I said, so NIST, that is the National Institute of Standard and Technology. So NIST is leading this initiative, and basically it's from US, and they have made a call for proposals on from the year 2016. So asking for persons across the globe, don't rely on mathematical problems like discrete log or the large prime number factorization. Instead, come up with some of the hard mathematical problems which a quantum computer never solve. Okay, so this is the real requirement that was provided by NIST, and almost the researchers across the globe started proposing their methods and ideologies, and there were several rounds run by NIST for many years. And in 2024, so there were only 4 standardized algorithms. Okay, so NIST has standardized only 4 algorithms as the post-quantum algorithms. So we will see them in detail in the upcoming slides. Okay, and as I said, so already governments have started migrating to the next spectrum. Okay, so meaning, so no, we don't want to rely on RSA or ECC. Let us go to let us migrate to something else. Okay, when the NIST standardized post-quantum cryptographic algorithms, every government started, okay, it's time for us to migrate all the data, whatever we use, we must migrate it to PQC algorithms. Okay, I will give you a flavor of what is PQC algorithms in the upcoming slides, but just for this slide, you just remember that, okay, so government started migrating towards PQC. Not only government, every top MNCs, they started migrating to it. Okay, and some of the nations which are pioneering in this migration as well as in the standardization process are like European Union, and then China, and then US, and India also. Okay, so India has a mission called NQM, where you have a basket of 6,000 crores being allocated, and you have 4 different pillars for this quantum initiative, and 4 thematic hubs has been created, and all these hubs are providing funds for these 4 pillars of quantum. Okay, so 4 pillars are mainly on the quantum computing, quantum communications, and quantum sensing, and quantum materials. Okay, so these are the 4 pillars, and for these 4 pillars, there were 4 thematic hubs developed across India, and they are funding startups who comes up with some novel ideas. And universally, we have some benchmarkings. Okay, so any company or any organization that can at least touch that benchmark, then it's perfectly fine. They can get the funds, right? And as I said, top giants like IBM. Okay, so they are the pioneers in the quantum computing. Especially, they have given free tier of Qiskit for years and years. But now it has been converted into an pay-as-you-go subscription model. Okay, so if you are really interested in playing around with quantum computers, IBM is giving you a choice that I think for a month you can run your circuits for under 5 minutes in their hardware. Okay, so the real quantum hardware, you can run them. It is not about simulation. So it is about you can take 5 minutes of the real quantum hardware to run your algorithm. If you develop something new or old, if you want to try, all you have to do is you just provide a credit card, and then you can create an account in IBM, and then you can access that hardware. Okay, but my suggestion to you will be like, so don't give credit card. Instead, try to download the community version of the Qiskit, run it in your own local laptop. You can simulate it and see whether your circuits are running perfect or doing it good. Okay, so if you get full command over your circuits and you have the full understanding of how it works, then go for IBM or any platform. Even AWS is providing you the quantum access in the name of AWS bracket. You have Azure Q. Okay, so Azure Q is nothing but it's offered by Microsoft, where you have access again to the quantum computer. The same is going for Google also. So these companies are offering quantum as a service. At the same time, they are spending millions and millions in developing quantum hardwares as well as algorithms. Okay, so yeah, so moving further, so we have till now we have talked about the advantage of quantum computer, and from where we started, how a classical cryptography works, and how a quantum computer can break them, right? So now moving on to the quantum cryptography. Okay, so classical cryptography is completely different. Post quantum cryptography is completely different, and you have something called as quantum cryptography in the middle. So quantum cryptography, in that the cryptographic principles what we relay will not be based on mathematics. Okay, instead we say that it is purely based on physics or quantum mechanics. So this is the reality with quantum cryptography. When you say a quantum cryptography, here the security is based on physics and not mathematical complexity. As I said, it is not going to rely on mathematical hardness. Okay, instead, it is going to rely on physical property of something. Okay, that something can be anything. Okay, so as I said, so right now in quantum cryptography, we are using, or we are relying on photons. Okay, so QKD is one of the predominant quantum cryptographic technique that what we use today, but there can be many that may come in future. Okay, so as I said, so it must be based on physics. There is no hard and soft rule saying that it's only for photonics or it's only with lasers. No, the answer is completely no. So it can be anything, but if it is relying on the physical properties or physics, then that can be brought into the quantum cryptographic domain. Okay, so and the key principles what we have here is the Heisenberg uncertainty. Okay, so you probably know about it. No cloning theorem. Okay, so what do I mean by no cloning? Okay, so and there is a property called no inverse. Okay, for example, let us say that, okay, so you have one with you. Okay, so and you are going to give me the inverse of what you have. So possibly what you will give me is, if you have one, you will give me 0. or if you have 0, you will give me 1, right? But in quantum computing paradigm or the quantum qubit, it will have both the states. Okay, so you will have 0 as well as 1. So there is no inverse exist, right? Okay, so there is you cannot say that, okay, since I have 0 and 1 with me, I will give you 1 and 0 or 0 and 1. Both are same, right? So there is no inverse exist. Similarly, no cloning theorem. So you don't create, or you don't have the provision to measure a state. I mean, store a state. For example, now you are listening to my lecture. Okay, so can I store this state of you? The state at what you are right now. You may be at rest, or you may be moving, or anything your state may be currently. I cannot store your state. If I am able to store your state, I can reproduce it, right? So you can take a copy of your state. But here, you are not having a provision to store the state. Okay, so you are listening to me and your state is unique. Okay, so this is the property of quantum mechanics. So since I cannot store your state, your current state, I cannot reproduce it. For example, the way I'm now delivering the session, if I am taking the same topic again, so will I be able to reproduce exactly 100% similar to what I did earlier? It's 100% not possible at all. There is no cloning. Okay, so there you cannot store a state, and hence you cannot copy a state. Okay, so these are some of the principles of quantum mechanics. We use that principles, okay, of quantum mechanics to build a cryptographic scheme that is resilient to any of these quantum computer or any computer you take, classical. Okay, so yeah, right now I would like to add a point here. Okay, so when I say our classical cryptographic system, they are prone to attacks by quantum computer. When I say post-quantum cryptographic algorithms, these algorithms are completely protected from attack that is being imposed by quantum computer. Meaning, if a quantum computer cannot breach these algorithms, then perfectly a classical computer can never breach that. Okay, but what is this in the middle? That is the quantum cryptography. So who will be able to breach this spectrum? Okay, so the answer is nobody can. So it's not about quantum computer. It is not about classical computer. Even if there is a new computer comes up, that also can never breach these cryptographic techniques, because it lies in the physical property. Okay, I have a slide where we will see how it is being achieved in the quantum key distribution. Okay, so yes, I think now it's time for us to switch to an animated version of BB84 protocol. Okay, so a quick question. So are we in sync? Can I have a yes or no?
Yes, sir.
Okay, thank you. Yeah. I will just switch to another presentation. Okay. Yes. Can you all see my screen? Is it visible?
Yes, sir. Visible, sir.
Yeah, the properties of light.
Yes,
so is
sir,
it the
visible.
screen or is, yeah, fine. Okay, thank you. So now, so what I'm going to tell you is like we have, or based on the properties of light. So the quantum properties can be realized in different things. As I said, so you take light, the minimalistic entity of a light, we call it as a photons. Okay. You take any other items, we say that it is an atom. Inside that atom, you say proton and electron. Okay, so all these things are the utmost finest quantity, or the quantity what we refer to. Let us take an example of light. Okay, so mostly all the quantum cryptographic algorithms what we use today are basically based on photonics. Okay, in that sense, they are using the photon and the properties of light to create or to simulate the cryptographic techniques. Okay, so here, based on the polarization, so we are going to see a version of how a photon is being used to generate keys. Okay, so that is what we call it as quantum key distribution, that is QKD. So today we are going to see the BB84 as a sample, so which is the globally recognized reference model for quantum key distribution. And so Yes. So now you can see there are two people. Okay. So you take any crypto or any algorithms in cryptography. We say there are two people, Alice and Bob. Okay. So you can see on the left you have your Alice, and on the right you have the Bob. Okay. So basically these are two cartoons. Okay. So I'm just reflecting these two characters here, Alice and the Bob the Builder cartoon. So now see when I say there is a photon. Okay. So a photon will have an entity. So basically a photon, if you send it in a polarization filter, okay, as you can see here, okay, so 1 minute, let me bring up my pointer. Okay, I think my pointer is not visible on the screen. Okay, so anyway, you can see there is an yellow light going up, right? So in the middle, you have your polarizing filter. So when you keep a polarizing filter, so when the light passes through the polarizing filter, so its direction or it takes only one version of it, right? So you can see on the unpolarized light, so before the polarizing filter, you can see there are two different dimensions. One is on the horizontal axis and one is on the vertical axis. When you send that light into a polarizing filter, now the horizontal axis is being dropped out and you are receiving only on the vertical axis, right? So when I have a polarizing filter that permits only the horizontal axis, then that polarizing filter will send your light sequence only on the horizontal axis and the vertical axis will be blocked. Okay, so this is the property, and what you are seeing an upside arrow that represent your vertical axis, and the green arrow what you are seeing is representing the horizontal axis. Okay, let us assume that Alice and Bob both are in a separated distance. Okay, and between the Alice and Bob, you are going to send light. Okay, that light when you are sending, so I'm saying that when it is on the vertical axis, it is going to take 1, and when it is on the horizontal axis, it is going to take 0. Okay, so now Alice has taken 1, which is on the vertical axis, and he wants to send that 1 to Bob. Okay, meaning, so now Alice has taken a photon, and the photon is right now in the vertical axis, and this vertical axis photon has to reach Bob, and Bob also must receive this vertical axis photon in his basis. Okay, you can see there is a plus on the blue and there is a plus on the red. Okay, so these are their bases. Okay, theoretically we say this as a basis. Now Alice want to send this one to Bob. Now the reality is, so if there is a polarization filter with Alice, and out of that polarization filter, if Alice is sending 1, the same will be received by Bob. If Bob doesn't have any filter, he just hold that photon, and if he measures that photon, he will get 1. Okay, so now if I want to send 0, the same. Okay, so you just send that same photon on the horizontal axis, and if the Bob is receiving that horizontal axis, perfectly fine. Now before they start this communication, Alex will tell Bob that, see, whenever I am sending anything on the horizontal axis, it is going to be 0, and whatever I am sending it in the vertical axis, it is going to be 1. Okay, so this they will communicate in the public channel. Like, okay, when they meet, they will convey, or Alice will loudly say Bob that, see, whatever I am sending in the horizontal axis, it is going to be 0. Okay, so likewise. So now, if this is the case, okay, so you have only 2 types to send. Okay, so when you have only 2 types, probably you will feel like, okay, so it can be easily, everybody can decipher the sequence. For example, if you say there is a vertical, there is only 2 possibilities. I can assume that verticals are going to be 1, or the other way can be verticals are going to be 0. So whomever receives this vertical, they will get to know, okay, so it can be either 0 or it can be either 1. Okay, so to add some salt to this conversation, so what they can really do is, okay, so yeah, before seeing that, okay, so let us see if Alice want to send 1101010 to Bob. Okay, let us take an example. So if she wants to send this, so what ideally she will send is, she will send 1, okay, so and then 0, again 1 on the vertical axis. So again, 0 on the horizontal axis. Again, 1 on the vertical axis. Okay. So this is how your conversation will happen. Okay. So we call this as a rectilinear basis. So what do I mean by rectilinear basis is like, so you have only horizontal and then you have only vertical. Okay. So now we are moving on to the next spectrum. So as I said, we are going to add some salt to it. So what I am going to add? Simply, I am going to have a change of 45 degree in the angle what I am going to send. Okay. As you can see here, the angle of basis, what I hold currently, I mean, what I had earlier was having 0 degree, which means there will be only horizontal, only vertical. Now I have shifted it with 45 degree. And what I must do? So it's very simple. I will have my 45 degree tilted for both my bits, right? So now what you are going to say is, see, when it is left 45 degree, it's going to be 1. And when it is right 45 degree, it is going to be 0. Okay. Now you can see here. Okay. So 1 second. So now Alice is having a basis which is tilted with 45 degree, and Bob is having a basis which is not tilted. So Bob is holding a basis which can capture only horizontal and only vertical. Now Alice is having a basis which is sending or which is going to send a photon which is 45 degree tilted. So what will happen? Any idea? If this one is being arrived here, what will happen? So this basis will not have the provision to capture that photon. Okay, it is like the polarization filter. I told you, right? So when the polarization, I say that if the filter is able to get only horizontal, it will send only the horizontal photons. Okay, all the photons that comes in any other dimensions will be dropped. If I say there is a polarizing filter that can send only the vertical axis, only the vertical will flow through. The same goes for your basis also. So here, if I am receiving something which is not on that basis, then 100% it will get dropped out. Okay. So we use this property also. So what now Bob has to do? See, he is not able to receive anything. So what he will do is he will try to change his basis. Okay. So he will tilt his basis and see whether he is able to receive something from Alice. So during the whole process, there will be a public classical channel. So where Alice will say, hey man, I'm sending you some bit. Okay. At the time, Bob will be waiting and he will be listening to see that, okay, whether any lights are being captured at my end. No, I am not able to capture anything. So what I have to do? Bob will change its basis. Okay. And he will see whether I am able to get something what you are sending. Now again, Alice will send. See, now the basis matches. Okay. And then now Bob also will be able to receive what Alice is sending. Okay. So already we have seen rectilinear basis. Now what we are seeing is called as diagonal basis. Okay. So you have now 4 variations. Okay. So 4 variations in the sense, in rectilinear, we have seen 2. One is horizontal and vertical. In diagonal, we have seen 2. That is left and the right shifted. Okay. So now, so this is how in reality the key exchange happens. Okay. So Alice will pick a set of bases and Bob also will pick a set of bases, and in every line, okay, so every line Alice will say, I am sending this, are you able to receive it? I am sending this, are you able to receive it? Okay, every line in a public channel, they will discuss. See, I am going to send something, are you able to receiving it? Okay, so Bob will change his basis until he receives some information on it. Okay, so now they both will do until they have perfectly matching basis for how many number of bits you want to transfer. Okay, so now both Alice and Bob have now fixed a basis. So now what will happen is, now Alice has chosen a set of bits to transfer to Bob, and Bob is also having the same basis. So Bob will perfectly receive all the informations what Alice is sending. Okay, so if Alice is sending 0 on the horizontal axis, fine, perfectly fine. Since the basis matches, they are able to receive exactly the same information what Alice is getting. Okay. So till this, any doubts? Are we going good?
Yes, sir. Yes, sir.
Okay, fine.
Yes.
Okay. So as I said, so how do they know about these bases? So basically, there will be a classical public channel. So where Alice will not say, no, you keep this basis. Okay. Alice will never say that you convert to that basis or this basis. They will not share the basis. Instead, Alice will say, see, I am going to send 1. Okay. So now Bob will change his basis and he will see whether he is able to receive that 1. Okay. Once he receives the 1 in that 1 basis, then he will say, I received 1. Okay. Then Alice will again send something on the same basis and Alice will say, I'm sending 0. Okay. If Alice is also getting 0 on the same basis, then perfectly now the bases have matched. Okay. So likewise, they will do first basis matching. When all the bases are matched, they will start the real communication. Okay. Now, the real problem comes in. Okay, so this is very, very similar to what is happening in our classical means. Okay, so once you have your keys and you are sending it to other fellow, no problem at all. Both the guys are now communicating over a spectrum and there is no problem at all. Okay, the real problem comes in when there is someone who is coming in the middle. Okay, in the middle in that sense, between your Alice and Bob. Correct? Okay. So now what happens is, see, now when the Eve comes inside or in between Alice and Bob, when you have already seen that, okay, so there is a polarization filter. When the photon is being transferred, when the light is being passed, when the basis changes or the polarization filter changes, it will not send anything on your right. Okay. What happens is when there is a guy in the name of Eve comes in the middle, when Alice is sending some bits in that axis, even if there is a 1 bit drop, immediately Bob will get to know that someone is there in the middle who has changed the basis. Okay, so this is the biggest advantage of quantum key distribution. So in other schemes, anybody comes in the middle, they can listen at least. Okay, but here, if anything happens in the middle, you will immediately get to know there is somebody in between us. Okay, Alice and Bob. Okay, so that is the real benefit of using quantum key distribution. Okay. So for example, you can see that the numbers what Alice is sending, okay, the Bob will randomly pick and verify so that they will get to know if there is a change. Okay. As I said, if the Eve in the middle, whoever has comes in the middle, if he is also using the same basis, the chance of basis calibration is probably 0, but still I'm saying if Eve is also perfectly having the calibrated bits, randomly when they verify for few bits what they are sharing, they will get to know somebody is in the middle. Okay, so there is no necessity that you need to be having a fear that somebody will hear our conversation or not. Okay, so that is completely not possible. If somebody comes in the middle, you will know perfectly that somebody is in the middle and you can immediately stop the conversation what you are doing currently. Okay, so this is how we say that it is perfectly secure. Okay, and we have already there is one more possibility also. See, when Alice is sending some number of bits, there is a possibility that Eve can record or Eve can capture whatever Alice is sending and he can send it to Bob. Okay, so this is something very similar to man in the middle attack. Okay, so he can lie in between and he can, so he can grab that, he can store it and he can send it to Bob also. Is it really possible? Is it really possible? What do you think? Any answers? It's perfectly no. Okay, so we have already discussed about it. Okay, so you cannot store a quantum state. Okay, so you cannot store a quantum state, or you cannot record, or you cannot reproduce any quantum state. Okay, so they are physical properties. Okay, so it is not at all possible. And finally, as I told you, so this whatever we have seen till now, so this is this is how a theoretical version of BB84 works. And practically we have BB84 kits. Okay, various vendors are providing us even in India. We have so many local vendors who are giving you the BB84 kit for educational purpose. So you can simulate and see, okay, so how the BB84 protocol works. Okay, so especially with laser beams. Okay, so we take a laser, and so to bring a photon, basically it's based on the energy equation. So you will lower its energy so that you equate it to one photon, and you will start sending it. You will be able to receive on the other side. Okay, so basically you will have the polarizing filter in the middle, and the whole protocols you can realize it in reality. Okay, fine. So are we going good? Can I have a quick yes or no? Are we
Yes,
connected?
sir. Yes, sir.
Okay, fine. Okay. So I have something just to keep you engaged. I have something, some activity that what we can do together. Okay. So it's a fun-based activity. So any idea? So the most powerful question during an online meeting that will really make you sweat. So any idea? Now, as I said, it's fun. Okay, so it's not so technical. Don't take that stand. Any idea? Any guess? Or do you want me to reveal the answer? Okay. So I believe, okay, so I believe I should reveal it. Okay. So it's about turn on your camera. Okay. So if it is an online meeting, most likely we always say that, okay, so we don't want to turn on our video camera. Okay. So likewise, so I have a really beautiful question. So do you know the height of Eiffel Tower in summer? Any guess or any clue? Any guess? Okay. Okay, I take an assumption that, okay, so it's not going interactive. So let me switch back to where we have started. So basically the height of Eiffel Tower is different in summer as well as in winter. Okay, so you can see that in reality in summer, due to the expansion of iron rod, so Eiffel Tower actually grows by 5.9 inches. Okay, so let us stop this interactive activity. Okay, so let's switch back to where we have, okay. So can you see my screen? Is it visible now? Slides?
Yes, sir. Yes, sir. Yes, sir.
Yeah, fine. Perfect. Okay, so now moving on to the quantum key distribution architecture. So we have seen the perfectly how quantum computer works, and I mean quantum key distribution works. So what are the components that we have in the QKD is the photon source. As I said, it's going to be laser. And then you will have a quantum channel where the photons will pass through. And you will have a classical channel where Alice will talk. Okay, so I'm sending you one. Okay, so that is a classical channel. And there is a detector. Detectors are the basis what you said on both the ends. Okay, so this is how it works. And how we can distribute these keys. Okay, so there are two predominant versions. So one is based on the optics, fiber optics, and the other one is based on the satellite. Okay, so these are the major research that is being carried out in the spectrum today. And the advantage and disadvantage of QKD is, so you say that the biggest advantage is its provable security, because it's completely secure, 100% secure, and there is no deviation, or there is no second thought. And it's perfectly intrusion reduction. If somebody intrudes, you will get to know. And it's purely based on physics. Okay, so these are the advantages. Since it is relying on the physics, we trust it like anything. Okay, and the predominant challenge is the distance is really limited, because as I said, it's going to be photon. Okay, so say I want to send a photon to a greater distance, it will fade out. Okay, it is like your visible light, it will fade out. That is the problem. And then the hardware what we use to do all these things are highly expensive. Okay, and then you have your photon loss and the infrastructure dependencies. Okay, so though the QKD what we are discussing right now doesn't require any specific temperature or humidity, but still it depends on the infrastructure, because you need a light source, a laser source, and you also there are some detectors which should be in place. They should be aligned. The filters what you use must be perfect, because all these things are infrastructure dependent. And moving on, so when it comes to the quantum security, I mean the implementation challenges. So hardware limitation is the first thing, and then your error correction and complexity. As I said, when you are sending a photon, okay, so you will have the polarizing filters. Okay, so the calibration itself is very, very tough. In reality, I'm talking about. Okay, so and in enterprise scalability, so it is really hard. Okay, so for example, when you set up a QKD kit, so possibly you cannot scale a QKD kit to generate, or for many industries if you have only a minimalistic version. Okay, so scaling it is highly difficult. And then you have your quantum algorithm development and the legacy system integration. So legacy system in the sense olden systems. Okay, so I cannot today I cannot say that no, I want to migrate it to quantum cryptography. So if I say so, then people will say, okay, you better invest 40 crores or 50 crores. Okay, so that is not something that every industry or every individual will really look at. Okay, so we want something that is affordable also. At the same time, that must be feasible by whatever I have invested already. Okay, so those were the legacy systems. So then you go for the transition to the post-quantum cryptography. So whatever we have discussed till now, they are purely based on the quantum cryptography. Now it's time for us to migrate it to the post-quantum cryptography. The reason being, why? Because I have invested money in classical computers. I have supercomputers. I have mainframe computers. Okay, I cannot say that, okay, see, since Peter Shor or Groover will easily find out the mechanisms behind, I cannot simply throw out all these machines, right? So I need something else which will run in my current infrastructure. That is the reality. Okay. So at the same time, so QKD alone cannot secure the whole internet, because we have machines which is running already, and we believe that they are pretty much good today. Okay, and we want to scale the top. Okay. So now, so what is a post-quantum cryptography? So these algorithms are completely secured against the attacks imposed by a quantum computer as well as your classical computer. Okay, and these algorithms must be able to run in your current computer or the classical computers. It is not about quantum computer. We don't want quantum computer to run these algorithms. Instead, my current infrastructure, whatever I am using right now today, these algorithms, post-quantum cryptographic algorithms, should be adoptable or should be taken directly to this infrastructure or the classical machines. This is the first point you must clearly understand. And then moving on, you have different families of PQC algorithms. So first is the lattice based, you have hash based, code based, multivariate based, and isogeny based. So every algorithm will have its own flavor, and the most possible or the most popularly used version today is the lattice based. So lattice is nothing but it's a two-dimensional plane where you have some dots and based on vectors between these dots. Okay, so that is how lattice means there is a two-dimensional plane where the dots are being scattered, and you create a mathematical hardness between these dots by defining vectors around these dots. That is how lattice-based mechanism works. And currently there are 4 standardized algorithm I said, so out of which 3 are based on the lattice, and we say that it is MLKEM and MLDSA. ML means module lattice. Okay. So real world migration challenges are so all the legacy systems should be able to run these PQC algorithms and the certification migration. Okay, so right now we have many flavors of cryptographic algorithms. So we need to say that, okay, so this is how a transition must happen. So that itself is a great challenge. And you have hybrid cryptography. So hybrid cryptography in the sense, I cannot purely say, okay, I will use only post-quantum algorithms for each and every use case. That is not going to work. There must be a clear classification of sensitive and non-sensitive. So non-sensitives, even today's classical algorithms can run, which is not at all a problem. And then you have your performance overhead. See, post-quantum cryptography algorithms are not performance-centric algorithms. They are security-centric algorithms. Okay, you say, for example, in WhatsApp, you are sending a message, and the same message is being delivered to your friend within nanoseconds. Okay, if you say that I have a post-quantum cryptographic algorithm, and if you send a message, possibly my friend will receive that message after 20 minutes. Then you will not be interested to use that algorithm, right? So there is a performance overhead. Again, it's in the research phase. We expect that there will be a drastic shift in performance. And also IoT limitation. So the main problem with IoT is they are battery powered and they are like bandwidth centric, right? So that is not that something that is very easy. And as I said, latency is a big player there. So you cannot say, or you cannot expect something to have a big number of latency. Okay. Fine. So some of the industries that are heavily impacted by which is highly interested in investing these PQC algorithms are like banking sector, defense, healthcare, cloud, and then blockchain spectrum. The reason being, so why cloud? So everything what we use today are cloud hosted. All the applications are being cloud hosted. So that is the reason all these players are expecting many solutions on the post-quantum cryptographic suites. And in India, so some of the initiatives are primarily driven by these giants. So ISRO, DRDO, and CDAC. And also India has a national quantum mission. So we have discussed this earlier. So that is also funding the whole projects or the entire spectrum of projects that is happening in the quantum domain. So quantum cryptography, post-quantum, as well as in the quantum computing. Okay. So, and some of the global initiatives include quantum communication, so quantum safe infrastructure and indigenous cryptography. Okay, so meaning, so you need to come up with your own solutions that can be scalable. Okay, and so I have planned for an activity. Okay, so let us do that. Give me a second. I will just bring it up. Okay, where is go? Okay. Okay, so can you all see my screen? Is it visible?
Yes, sir.
My browser window?
Yes, sir. Yes, sir.
Okay, fine. So we have talked more about the NIST standardization and other things. Okay, so as I said, the main important factors, so NIST is the real player, and you can see in August they have standardized the algorithms. So this is the trustable page what you can always refer to when you want to work on the post-quantum cryptography. So you can come up or you can come here. Okay, so you can see this post-quantum cryptography standardization project. Okay, so you can see all the projects. So whatever has happened. So what was the call for proposal? Okay, round 1 submissions, round 2, everything is open. Okay, so whatever the number of proposal they have submitted, all the supporting files, everything is available in this website itself. Okay, so if you plan to progress your research in post-quantum cryptography, my sincere advice, don't rely on any publications. Come to this site straight away, dig deeper, and you will get to know the real numbers, the real pictures. Okay, there are many research articles available, but my sincere suggestion to you would be like, so don't rely on those articles. Come to this website. You just see through all the submissions across these years. You will get to know. For example, you take any number of submissions, you can see all these supporting documents. Okay, so who are all the players, So what is the submitted? Okay, so what was the comment they have received even in that round? So how it is vulnerable? All these informations are officially available within this website. Okay, so you just, what you have to do is you just click on, I mean, you just search like NIST PQC standards, then you will be taken to this website and you can see on your right, everything is available. And also there are some webinars. Okay, so that is also available on your right. So, okay, so you just have to surf through all these links and you will get to know the real picture of what is done and who are the real researchers. Okay, my sincere advice, again, I am repeating, don't rely on any other research articles over this website. Okay, so that will give you the better understanding. So now, okay, so it's time to say a thank you. So thank you so much for listening. So any doubts or
Yes, sir.
queries? So I
Yes,
believe
sir.
I have taken the stipulated time.
Yes, I will open the floor for questions from
Yes,
participants side, sir.
perfect,
Yes, sir.
perfect.
Yes, sir.
Thank you.
Yes, sir. Yes, dear participants, do you have any queries? Do you have any questions or clarification about this session? If you have anything, means please ask him. Sir is here for explaining us. If you have any doubt, please ask. Yes, sir. So, on behalf of this organization team and all of the participants, I extend our sincere gratitude to Dr. Rajakumar Arul for delivering such an insightful and informative session on quantum cryptography and post-quantum security. Your valuable insights, clear explanations, and expert perspectives have greatly enhanced our understanding of this important and emerging domain of quantum technologies. This session was truly enriching and highly beneficial for all of us, sir. So thank you, sir, for sharing your time, knowledge, and expertise with us today. We are truly grateful for your valuable contribution to this faculty development program, sir. And I'm sincerely thanks to explaining that website also, sir, like NIST PQC
Yes,
standards. Yes, sir, yes, that's very useful for us, sir. Yes, thank you so much, sir.
most welcome, ma'am. Most
Yes,
welcome.
yes, thank you, sir. Yes,
Okay, ma'am. So if
yeah.
there are no queries, then probably we can wind up.
Yes, sir. Yes, sir. Thank you so much, sir.
Fine, ma'am. Thank you.
Thank you, sir. Thank
everyone.
you, sir. Yes, sir.
So thank you, Professor.
Yeah, thank you, sir. Thank
Yes,
you.
And dear participants, I have one request for all of you. So at the end of each session, we have posted that feedback form link. I request everyone to complete that link. That is, you submit that form, then only we can assign attendance for that. Okay. So you make sure that you need to maintain minimum 80% of attendance. Then only you are eligible to receive that certificate. So once again and repeat, you need to submit that feedback form we have posted on that chat box at the end of each session. And I request all the participants to rejoin the meeting by 1:25 p.m. because our next session will begin promptly at 1:30 p.m. Okay? So please rejoin the meeting by 1:25 p.m. Now we will have time for lunch. So please rejoin the meeting by 1:25 p.m. Yes. Thank you.
All of you start right. Don't waste your time.
Yes, very good afternoon, everyone. Welcome back to the post-lunch session for our FDP. I hope the break has refreshed you all. Thank you for rejoining on time. We are happy to everyone to stay connected and gain maximum benefit from the expert insights being shared today. Now, it is my pleasure to introduce our distinguished resource person for the session, Dr. R. Dinesh, who is currently serving as an assistant professor at Indian Institute of Information Technology, Design and Manufacturing, Kanchipuram. Dr. Dinesh completed his master's degree from Indian Institute of Technology, Guwahati, and earned his PhD from Indian Institute of Technology, Kharagpur. His research expertise spans several advanced domains, including Internet of Things, wireless sensor networks, edge computing, deep reinforcement learning, federated learning, quantum machine learning, and 6G vehicular networks. He has made significant contributions in areas such as intelligent resource allocation, AI-driven IoT systems, and next-generation communication technologies. Today, he will be delivering an insightful session on the topic Classical Federated Learning to Quantum Paradigms, Core Concepts and Limitations. We are delighted to have him with us today. Now, I invite Dr. R. Dinesh to take over the session. Please, sir.
Hello, am I
Yes, sir.
audible?
Yes, yes, sir. I'm audible, sir. You're audible, sir.
Yeah. Thank you
Yes.
for the introduction, ma'am.
Yes, sir. Thank you, sir.
It's I thank organizing team for giving me this opportunity.
Yes, sir.
And today I'm going to present on the topic of classical federated learning to quantum paradigm, core concepts and limitation.
Yes, sir.
Just give me a second, ma'am. I will share my screen.
Yes, sir. We are ready.
My screen is visible, ma'am.
No, sir. Not yet.
Just a second, ma'am.
Sir, we are waiting, please. Yes, sir. Dear participants, we have one small request. We kindly request you to all submit your feedback form. At the end of each session, we have posted feedback link. You please submit. Thank you.
Yes, my screen is visible.
Yes, sir. Now it's visible. Yes.
Yeah.
Yes. Thank you, sir.
Thank you, ma'am.
Yes.
Okay. So, good afternoon, all. So today I'm going to present on the topic of classical federated learning to quantum paradigm, the core concepts and then limitations. So I have divided my topic in majorly into four subdivisions, the introduction about the quantum computing, and then the basics, and then we have to learn a few things about the quantum circuits, and then like we just start we will just know the basics of machine learning and then federated learning, and then we will jump into like a quantum machine learning and then the federated learning architecture, and then finally we'll conclude with the limitations and the future directions. So this is my outline for my today's lecture, and first we'll start about like why classical computers reaching their limits. So as we know the Moore's law. So Moore's law saying that like every 2 years like we are every 2 years there will be scaling in the the transistor size will be reduced, and then the performance will be doubled in every 2 years. But with the advancement in the recent years, like it is already went to the nanoscale. It is already went to the nanoscale. Now what will happen is now we want to improve the performance, and also we need to reduce the transistor size. So in this case what will happen because of the because like usually how we are transferring the data, we are how we are storing the data, we are storing the data in the form of classical bits like zeros and ones. So because of the reduction in the size, and also we want to improve the we want to improve the performance, like that means processing speed. So there is electron leakage is happening. So because of that reason, like we can't able to move further in the sense, meaning like we can't able to reduce the transistor size further. So we will reach the threshold, like after that Moose it's indirectly we can say that Moose is failing. We can't able to if you see the past years, like what will happen, like every 2 years transistor size will be reduced, and also the performance the performance and then the performance will be doubled by every 2 years. So that is one disadvantage. And also like we know like what is the we know our traditional uh, classical computers works on the principle of Van Neumann architecture. So, what do you mean by that? Like Van Neumann architecture in the sense, so we know there will be input units and inputs, and then the processing unit and then memory unit. So, in order to perform any single instructions, so what we need to do is like we need to take the instructions from the hard disk, and we have to put it in the main memory. So once we put it in the main memory, then only we can able to execute the instruction. So this is how like a uh, classical system works. So because of this one, like what is happening, there is a bottleneck in memory. If you see the processing speed of the CPU is dramatically high, and also retrieving data from a memory, it is somewhat low. So to transfer the data from like a hard disk to main memory and to process the data, it is taking little time. So there is a bottleneck. So even though our processors is capable of processing the data much faster rate, because of that memory bottleneck, like we can't able to do it. We can't able to do it like we can't able to do process the data much faster. So this is one bottleneck is it. So and also like we have certain other limitations are there. Like let us like take like some cryptographic algorithm. Like so, whatever the classical like whatever the cryptography algorithm are there, it's basically works on the basically two it is working on two things. Like one is with the help of the prime factorization, and another with the help of the like the prime factorization is one of the important concept, and another one is a hash with the help of the hash. With the help of the two things, like the cryptograph the two. So once the message is encrypted, so to decrypt the message, like we are using the concepts of prime factorization. So to decrypt it without the primary without the public and private key. So in the classical computers, like it will take like so much time, like or because the prime factorization is not easy to decrypt the data. So this is one disadvantage. But in case of quantum computing, what will happen? Like so, I will explain. Like it will run parallelly. So if you run parallelly, like what will happen? Like you can process the like we will decrypt the data like, much faster than the classical systems. And also like parallelism is like is a is a big problem in case of classical computers. Why? Because like we have only two states. We can store the data in the form of only two states. Either it will be in the form of zero, or else it will be in the form of one. So that means like if you talk about the transistor point of view, you can able to store either in a high voltage or else in a low voltage. So that means like parallelism is possible between two states only. Like apart from that, we can't able to do much more parallelism. So the parallelism concept is limited in case of classical computer. So but the same thing, like if you go for like mm, these are like certain limitations of classical computer, like the limitation constrained in the form of physical, architectural, like architectural and then computational limits. So these are the motivating factor for the cloud computing. Now we will see like why we need a cloud computing. So as we already told, like like Moore's law is failing. Moore's law is failing in the sense, meaning like we can't able to. So we have reached a certain threshold. We reach a certain threshold. Further, we can't able to reduce the transistor size. Further, we can't able to reduce transistor size. Meanwhile, like whatever the transistor size we have reduced, there it is perform some electronic leakages. So this is a limitation. So because of limits, like now we are trying to solve with the help of the photons. Like with the help of the photons, like what they are trying to do is like so I will tell like how this problem is resolving. Now we will see some other problems, like as I already told, like in the cryptography, like the prime factorization is one of the important concept in the cryptography and hashing. So this to solve the prime factorization problem in the classical computer, it takes like uh, at least like some huge amount of time it is needed. But in case of quantum computing, the time we can reduce, like within short time we can solve that problem. And also like a classical computer data will not be able to solve the complex patterns. And also for large scale data, we can't able to like high dimensional data, it is not possible to solve in case of classical systems. So these are the challenges there in the classical systems. So to address this one, like we are going for the quantum computing. And like these are like so certain application where this quantum computing is using in the drug discovery, and then material science, and also in genome what we will do, there will be genome pattern will be there. So to find the traits of a human being, there will also we will use a quantum computing, and also financial data, stock predictions and financial data, and also it will be used banking sectors. So there we will use a quantum computing. So because of the high speed, there we will process the data, millions and millions of data we can process within a short time. So I already told these are some disadvantages, how we overcome it. So before going to what is quantum computing, so we have to know what is qubit. So as we know, traditionally, how we are storing the data in case of classical computing, we will store the data in the form of bits. So bits in the sense, either we can store it in the form of 0 or 1. So in case of transistor, if you are saying either we can store it in a low voltage or high voltage. But in case of quantum, it is also you can able to store a low and high, but also in the intermediate states. In the intermediate states, in the sense the wherever I've seen an example, they have taken an example of flipping a coin. So what will happen? What will happen if you flip a coin? What will happen? It will flip. So either what the classical system will understand is after once it fall down, we will get the result, right. Either you will get 0 or else you will get a 1. So those are the states we can able to store in the form of classical system. But in case of a quantum system, what will happen? You can store the intermediate state, whenever you're throwing a coin. So whatever the intermediate states are there, even those information you can able to store with the help of a qubit. How we are storing the information, I will explain in the next slide. So and also here, in the case of a classical bit, it is a deterministic in nature. So deterministic in the sense, you can find the states. The states, either it will be in an high or else low. That means it will be either 0 or 1. But in case of quantum, so as we are storing the intermediate state, the middle, whatever the state will happen, it is a combination of both high and low. So those states we can call it a superposition state. So if it is high, if it is a high, high means we can represent 1, or if it is a low means we can represent 0. If it is a combination of both high and low, we can say it is a superposition state. And so in case of, so in classical computer we will use a bits. In quantum we will use a qubit. So this qubit will give a chance to do the parallelism. And so the qubit is a basic, with the help of qubit is a one of the basic principle. So with the help of that, the quantum on top of that, we have built the quantum computing. So with the help of the qubit, we also help for the parallelization. So how we are storing the superposition state, in the sense here the side represents the quantum state. So the quantum state will be represented in the form of, so usually we can call this notation is a diarc notation. So this notation we can call it a diarc notation. So this is the quantum state, and alpha. So usually whenever this bracket is there, whenever this bracket is in the closing direction, we can say it is a gate. If it is there in the opposite direction, we can say bra. So if if you have closing and opening in the same direction, then we can say it's a bracket. So it's a bracket. Bracket means we everybody knows, right? Like a bracket in the sense it is a notation where we will store certain variables. So similarly, the same concept only in the quantum also. So if it is in this if it is in the right side direction, we can say it's a gate, or if it is in the left side direction, we can say it's a bra. So we can say it's alpha 0 gate and plus beta 1 gate. So usually this is, we can say, is a diarc notation. So what it represents is in the sense like it is a combination of both high and low. Okay, it is combination of both high and low. That means like the 0 is a high, 0 is a low state, and 1 is a high state, and alpha and beta are the probabilities of getting low. Beta is like probability of getting high state. So that means like this is, we can say, it's a quantum states. So we everybody know like how bits will be stored. The bits will be stored in the form of zeros and ones. Next, we will see like the introduction of quantum computing. So the quantum computing. So the basic principle of quantum computing is like qubit. Okay, so we can say it's a qubit is a basic unit of quantum computing. So, and on top of that, like here we have a three major phenomena, like three properties are there. So what are the properties? Are superposition, entanglement, and quantum interface. So like we will see like what is superposition. So, like superposition is nothing but like so as I already told, with the help of diarc notation, we can able to store high and low, like a combination of both high and low with the help of the superposition state. That we can say it's a superposition state, and the entanglement is nothing but if you know like a state of one bit. Okay, you can automatically able to find a state of another bit. Okay, that we can call it like we will see an example like what is what. And the quantum interface is nothing but like whenever you are sending a data, or whenever you are with the help of the quantum you are sending a data, there might be chance that like it may interfere. So to overcome this, like we will use a error correction, or like error correction, quantum error correction and all. They were like it is like quantum error correction, they will correct the errors. So with the help of these three phenomena, like we are enable the parallel computation and potential exponential speed up. So the applications where we are using here is like cryptography we are using, and the optimization problem we are using, and then like quantum machine learning we are using. So the next is a quantum superposition. Say as I already told. So in the qubit, like we can able to store both high and low state. So how it is possible? With the help of the quantum superposition concept, with the help of that, like it can able to store both high and low bits. So that means like a qubit can exist multiple states simultaneously. The example which I told is throwing a coin, right? So in the throwing a coin, like what we are doing, like we are storing the intermediate state in the sense like we can't able to determine like until unless in the circuit, if you measure that one, we can't able to say whether it is in a high state or low state. So once we have measured that value, then we can able to determine whether it is in the high or low state. So that is also not a correct value, but the thing is like at that, like which one is having a higher probability, we will get that value. So it can be either high or low. So like in our measurement like in our measurement circuit, like either like whichever the probability is high, that we can able to get it. So as I already told, this is our diarc notation. So with the help of this one only, you can able to store the quantum states. So that means like psi is equal to alpha 0 plus beta 1. And alpha and beta are the probability amplitudes. And one condition is here is like as we know, like sum of all the probabilities, it should be equal to 1, right? Similarly here also we can say the sum of the the alpha square plus beta square should be equal to 1. Okay, this is like this kind of a standard condition. So that means like whenever you get a probability amplitudes, so if you are squaring and summing the values, you will get a value is equal to 1. And the superposition like enable quantum parallelisms. Why? Because here we are not only storing the low and high value and also intermediate states. Okay, so that intermediate states, the like how, and one more condition, one more thing is like how many intermediate states we can able to store. Like that depend upon depending upon the circuit, that depend upon the circuit like which you are having. Like usually so in order to find like superposition state, we will use a Adamant gate. So like we will see like what the Adamant gate and like what are the different types of circuits we are using. Like all the thing we will see one by one. So but one thing you have to remember is like the probability of the amplitude should be the alpha square plus beta square should be equal to 1. The next one is a quantum entanglement. So even the quantum entanglement is also similar concept. But the thing here is like if that means like with the help of the quantum entanglement only like they are like saying like either one person can sit in India and another person can sit in like other side of the world, like let us take like USA. They can able to transfer that information from India to USA with fraction of seconds. That means like if you are changing like any state, if you are changing like once, if you are changing a state like a qubit state from here, that information that whatever the changes you are making, that will be automatically reflected in USA. So this is like for understanding, I'm saying like the quantum entanglement is nothing but like whenever you are changing like one qubit state, that will automatically correlate that in simple ways, that automatically able to identify what will be the next qubit state. So the here the clear meaning is told is like the state of one qubit instantly influence the state of another regardless of distance. So the example which I told that means like with the help of the quantum entanglement, you can able to transfer the data. That is a behavior. That is a property. Or else you can call it that is a behavior. And how we are doing with the help of this symbol, like we can so we can say this is a Bell state. So the Bell state is representing like both both low plus high divided by square root of 2. So as I already told, the entanglement enable the powerful applications such as quantum communication and teleportation, and then quantum computing speeds. So the communication will be like once the quantum is in the top leap, like the communication will be happen in a fraction of second. So now like how the communication is happening, we are transferring the data to nearby ISBs. From there it will it will be sending to the satellite. From there it will send to the from the satellite to satellite communication will happen. From there it will send it to the nearby ISBs. From there you will get it to the receiving end. This process and all will not be needed. So once quantum become once the quantum is like in the full leap, like what we can do, like we can transfer a data in a matter of seconds. We can able to transfer it in a matter of, not in a matter of seconds, like milli or less within less time, like you can able to transfer data. Okay, and we will see like why we need a federated learning. So before going to like why we need a federated learning, like usually we will say like how in order to transfer it, like how we will transfer data, in the sense like in any architecture if you're taking, like usually like we will use a client server architecture. So that means in the client server architecture, what will do, the client will produce the data, it will send it to the server. In the server where actually we will have a machine learning models will be there. There we will compute the data. So there we will compute the data, and then whatever the results we are getting, we will send it. We will send the response to the client. So this is how like traditionally traditional learning will works. But in case of federated learning, like it is not a centralized approach. It is not a centralized approach. It is kind of a decentralized approach. Like here, here we will have like more the here what we will do is like even the clients will having the clients are having like machine learning model. Like so let us having like three clients are there. So three clients will run the machine learning model independently. So that means like it can make a decision in the client itself. So once we made a decision, what we need to do is like we need to we need like whatever the model is learned, whatever the model is learned, those information we need to send it to the server. So that means like it is not a raw data, it is kind of a metadata. Metadata in the sense like a whatever the model learned, those information we are transferring to the server. We are not transferring, like we are not sending the raw data. Now in the federated learning, what we are doing, we are sending a metadata we are transferring. So this will solve the privacy violation. The privacy violation in the sense like we are not sending a raw data. Like instead of the raw data, we are sending the whatever the model learned, and whatever the model learned output we are transferring. So that means it will for the sensitive data, the privacy violation will not be violated, and the security risk will be reduced, and also data breach will not be there. Data breach will not be there. And also like I am just sending like we are just transferring uh, like metadata. Even if you are encrypting the metadata, like the even like if you're encrypting the metadata, like they can't able to identify what we are sending itself. So where we are doing this kind of thing is like GDPR we are sending, and HIPAA we are sending. Like usually these are like sensitive data, though they are not willing to share it to the they are not usually share with the help of regular data transmission. So for these cases, like we will use a federated learning. And also in case of IoT and edge devices, so there we will have like enormously we are producing lot amount of data we are producing. So instead of making the architecture in an centralized one, so we can give a computing power to the edge, and also fog, and also to the server. So what it will give is something like instead of transferring all the sensitive data directly to the server, we can train with the help of whatever the data we are getting. We can train the data in the edge and also in the fog. So once we train, the model is the whatever learned from the whatever we learned from the uh, data. So that means like we can simply say it's the hypothesis. We can transfer the hypothesis to the we can transfer the hypothesis to the server. The hypothesis in the other name of the hypothesis, we can say it is a metadata. So we can say the metadata to a like say, basic information. Like we are not transferring a raw data. Instead of the raw data, we are training in the edge device itself. Once edge device is learned from the data, those information we are transferring. So this will reduce the privacy violation and also the security risk and data breaches. So and like how like so the example which I gave, like given like three clients. So how in the sense like each will be learned based upon the local data they are having. So all the local data based upon the local data, it will be trained. Based upon the local data, it will be trained. Once we send it to the server, so it will aggregate all the model, like it will get the information from all the clients. So what it will do is, like, it will aggregate the data from all the clients. It will do the average of thing, like we will have certain model updaters are there. The simplest one is a average one. Like we will an average of all the models, and then what we'll do is train the we will train the server, and whatever the server is there, if there is any changes there, that changes will be transferred back to the clients, so that the clients will get to know, like, how other clients are performing, based upon why. Because as a client, the client knows the data from the own sensor data. It doesn't aware of other edge devices, what the data it got. It doesn't aware of it. So for the cases, like what we are doing, like we are updating the model at the server, and we are transferring the updated information to the each and every client devices. And these are the challenges of federated learning. Here we have like centralized data storage exposes to a sensitive data. So these are some challenges, like how we are overcoming that one. How we are overcoming, like we are training in each nodes, like nodes in the sense, like as I already told, like the client, in other name you can call it each node, in term of in the sense of IoT, we can call it as a node. Means like a device which is present near to a sensors, uh, like we can call that one as a node. So instead of centralized storage, like we can perform like distributed storage. Not only distributed storage, like distributed computing also we are giving. And also risk of cyber attack and data breaches will be placed here. So where we can use here is, like we can use it in the healthcare and finance, and in IoT we can use it. So the problem with this, what we are addressing is there is a certain database problem in the centralized approach. So instead of using a centralized approach, we are going for the distributed approaches. So with the help of the collaborative distributed learning. So the collaborative distributed learning is like each client will learn from their own data, and those learned information will be sent to the server. Server will collect all the information, and then update the will update the model, and it will be sent back to the. So whatever the updation is there, again, like clients will get to know that. Okay, so right till now, like we have seen, like the essence of our topic, like what is quantum computing and what is federated learning, and like how we are going to use it in the quantum computing. We will see after learning the some basics of the quantum circuit, like some basics of the quantums. So next we are going to learn about the quantum circuits. So just like we have like um, just like we have gates in case of uh, classical bits. Like similarly, here we have certain gates are there. Certain gates are there. We are not going to see all the gates. Like we will see some important gates. Let us see some of the basics. So usually, like we can say, like classical bits are like classical bits data. Like what we can say it is a irreversible. Meaning like so like meaning like let us take like a AND gate. And in case of AND gate, like we are getting output as 1. So in case of output is 1, like we can able to say what will be their inputs. What will be the inputs we can able to determine 1, or like whenever we will get 1 and 1, then only we will get output as 1. But let us assume we are getting an output is 0. So from this, like we can't able to determine what will be the inputs, right? Like either it can be 0 0 or 0 1 or 1 0. So that means like from the output we can't able to determine like so that means like once we get the output, like from that, like we can't able to determine what will be the input. So this is one problem in the case of classical bits. So to avoid that one, like we are using only certain gates in the quantum. So those gates, what will do, it will make it reversible, and also it will be like a unitary matrices. Like so reversible in the sense, like whenever we are taking the inverse of it, you will always get as unitary matrices. So whenever we will get a reverse of that operation, we will get a unit matrices. So those are the concept will be very much helpful for the identifying like what will be the state, like what will be the other state. Like if I know one qubit information, one qubit information, from that, like I can able to determine what will be the other qubit states. So, and also like with the help of the quantum gates only, we are enabling the superposition concepts, entanglement, and then quantum computation and all we are performing with the help of the quantum gates only. So like common quantum gates are like Pauli X gate. So in Pauli X gate, what we are doing is like we are flipping the qubit state. We are flipping the qubit state. It is just like a not gate for understanding I'm saying not gate, but it will have some in the not gate it doesn't have imaginary data and all. But in case of poly X gate, like we have like for imaginary data also, we can able to flip the, like we can able to flip the state. Like if it is a 1, you can able to flip it to 0, or else with the phase rotation also we can able to do with the help of a poly. Like we will see what is what in the next slide it is there, like we will see what is what. And also with the help of the adamant gate. So adamant gate, like with the help of the adamant gate only, like that superposition concept is achieved with the help of the adamant gate. So how we are achieving that? Like usually the adamant gate will be represented in the form of symbol H. So like how we are achieving that one? Like so as I already told, like there will be some probability of getting high, and there will be some probability of getting low. And so those things like state 0 plus state 1 divided by square root of 2. Okay, that we can call it the adamant state. Here, if we see here we can call. So this is for state 0, adamant of 0. This is the state representation, and similarly for adamant 1 also the same thing. So that means like with the help of adamant gate, like for simple intuition, I'm saying. So it can the probability of getting high will be 50%, and similarly the probability of getting low will be 50%. So this is on behavior. With the help of that, like we are achieving the superposition concept. And similarly C naught gate. So the C naught gate, what we are doing is we are generating the entanglement between the qubit. So as I already told, so entanglement is nothing. If you know state of one qubit, you can tell the what will be the state of another qubit. And also with the help of the entanglement concept only, like as I told, right, like we can able to transfer data from one corner of the earth to another corner of the earth. So how we are achieving that one? With the help of the C naught gate. With the help of the C naught gate, we are achieving those concepts. So let us see an example of poly gate. So as I already told, like poly gates are the fundamental single qubit unit state. This is a single qubit unit state. So here, like we will have for single state, for single information we'll have. So it can be represented as poly. There are 3 different types of poly gates are there: poly X gate, poly Y gate, and then poly Z gate. So we have three different types of states are there: poly X gate, poly Y gate, and poly Z gate. So what the poly X gate will do is a bit flip operation. So here we will flip the bits. Here we will flip the bits, and the poly Y gate, there what we will do, there we will flip the bit and also phase also. So that in case of X poly gate, what you are doing, we are flipping only bits. But in case of Y poly gate, what we are doing, we are flipping both bit and the phase. Phase in the sense like the direction we are changing. Like let us assume like initially it is in the zero position. So after flipping, it will be in the 150 on shifting of 150 180 degree phase shift. If we are doing like 180 degree, it will be there. And similarly, Z polygate, what we are doing, we are there we are only doing the phase flip only. So basically, the polygates are essential quantum operation used for manipulating the qubit state. So usually the Shor's algorithm and like what discharge algorithm all will use the concept of quantum circuit. Basically, so in order to implement quantum algorithm, so the quantum gates will be essential to go. So with the help of the quantum gates, we can create a quantum circuit. With the help of the quantum circuit, we can create the quantum operations, like quantum computation we can be able to perform. And the next gate we are going to see is the Adamant gate. So as I already told, like the Adamant gate will be represented with the help of a symbol called H gate. So it is a fundamental single qubit quantum gate. So as I already told, like it creates a superposition state from a classical base state. So it creates a superposition state. So that means like whenever we are having a bias state of 0, so if you're passing to a Adamant gate, so we will get a 50% of probability of low and 50% of probability of high. Similarly, if you have a high state, if you're passing to a Adamant gate, then also like we will get a like 50% probability of low and 50% probability of high. So this is like quantum parallelism can be achieved with the help of this. So like how the Adamant gate matrices will be represented. This is like Adamant gate matrices representation. So quantum circuit representation, as I already told, like it will be represented with the help of the H symbol. So one thing if you have to observe here, like with the help of the Adamant gate only, we are achieving the superposition. And also, so superposition is one of the important concept in quantum computing. So once with the help of that can be delivered with the help of the Adamant gate. Next, we will see about C0 gate. So next is the C0 gate. So the C0 gate, we can call it a controlled NOT gate. So till now, whatever we have seen, it is all are kind of a single state with the help of like a single state information, like it means like with the help of single state we are achieving, like whatever the Adamant gate and whatever poly gate we have seen, it is kind of with the help of a single information, like that means you will pass single data. That means single data, either it is 0 or 1, you will pass it. But this is kind of a cube. C0 gate is kind of a 2-qubit quantum gate. So it consists of, one is a controlled qubit will be there, and another one is a target qubit will be there. So the target qubit will be flipped only whenever the control qubit is 1. So that we will explain you with the help of the truth table. So that means like the meaning is very simple. Meaning is very simple. Whenever control qubit is high, during that time only flipping of data will be happen. So whenever the qubit is low, like whenever the control qubit is low, during that time the flip will not happen. Whatever the input state is, that same will be the output state. So whenever the control qubit is high, so that time only flip operation will takes place. So if it is confusing, like I will tell you in the truth table. So see here, like here both are like the first one is a control bit. In the control bit, like both bits, first two states are like control bits are zero. Like if you see the target on 0 and 1, so even the output targets are, so output target will be 0 and 1 only. There is no change. Whatever the input data, like how the input target is there, output target also looks similar or looks identical. You can say like that. Now see, like whenever the control bit is 1, whenever the control bit is 1, now just check the target bits. Now here the target bit is 0. Sorry. Here the target bit is 0. Same if you see the output target, what will happen? It is flipped. Correct, right? Here the input target is 0, output target is 1. Similarly, here for control bit is 1, if the target is 1, what will be the output target? Output target is 0. So this is, in this way the C naught gate is performing. So that means like in the matrix representation, how we can say this is like so let us assume this is a controlled, this is control gate, like is in this one 0, this is a control gate, and this is a target qubit. So that means 0, whenever the control bit is 0 and target bit is 0, output is 0. There is no change. And similarly here also 1. So whenever there is a change, is at that time only it is flipping. So here, like control bit will be represented with the power dot, and the target will be represented with the power the XOR symbol. XOR in the sense like circled addition. Circled addition, you can say it. So the target bit can be represented with the power circled addition, and the control bit can be represented with the power dot now. So these are like, so why it is needed, like this is essential for quantum algorithm and quantum communication. So used for the building the quantum circuits. So basically, like so one beauty of the C naught gate is it is following the reversible property, and also it is a unitary, like not only this C naught gate, take any gate in the quantum, okay, all gate having the behavior of unitary matrices. So if you reverse the, if you're doing like a inverse of this C naught gate, if you're performing, then you'll get a unitary matrices. So C naught gate enable the quantum operation play a major role in creating entangled quantum state. Next, we will see about the block sphere state representation. So as I already told, like we are having superposition states are there. So till in case of classical bits, you can able to represent either in none, 0 or 1. But in case of quantum computing, you need to represent the qubit representation, you need a block sphere. The block sphere is essential for representing the states in case of quantum computing. So how we are doing that done, like as I already told, like the quantum state can be represented with the help of the alpha 0 plus beta 1, where alpha square is equal to 1. Okay, like, so this is the basics. This is the basics, like how many times we are studying the quantum computing. So every time, like, we have to keep the mind in the sense, like, quantum state can be represented with the help of the alpha low plus beta high, where where amplitude squares, the probability amplitude squares, sum of the probability amplitude squares is equal to 1. And also, like, if you want to represent in the form of parameterization, so, like, how will represent? So, sorry, I forgot to mention this one. Like, the Bloch-Beer representation also, you can able to represent the state information. With the Bloch-Beer parameterization also, you can able to represent the state information. So basically, like, this will be helpful to this. Like, previous state will be known for whether we are flipping the data or not. So this the Bloch-Beer parameterization, from this, like, you can able to know whether we are doing the angle flip or phase flip, or any flip we are doing in the form of angle or phase, that you can be with the help of the Bloch-Beer parameterization. So here, what it means by this is the quantum state is equal to cos theta by 2 ket of 0 plus e I power psi sine of theta by 2 ket of 1. So it can that pi can like theta can be 0 to 5, and psi can be, like, it can be represented from 0 to 5, like 360-degree you can be able to perform this psi. The shifting operation can enable only for the pi directions. And these are the the representation of states. So, like, state 0, state 0 can be represented in the north pole here, and the state 1 can be and in case of like coordinates, like, if you take coordinates, we can represent 0 0 0 1. In the Bloch-Beer, like, a 0 will be represented in the form of 0 0 1, and 1 will be represented in the form of 0 0 minus 1. So otherwise you can call it the south pole. And the plus, we can represent it, like, the superposition state can be represented like a 1 by root 2, like a ket of 0 plus ket of 1. So this we can say is a positive x direction. So this is here. Positive x direction is, this is a negative x direction. Exactly opposite here, we will have a positive x direction. So negative x direction, this is the negative x direction. And y direction is the imaginary value. In the imaginary value, you are using I plus I, like, that will represent in the form of y direction, positive y direction, and the negative imaginary value can be represented in the negative y direction. It's exactly opposite to positive y. And similarly, z also will be represented. Z will be represented here, and so that means, like, a 0 and 1. So, like, so basically, like, the Bloch-Beer will able to visualize where our bits are actually storing, like, in either it's x-axis it is storing, or y-axis is storing, or z-axis it is storing, on which angle it is storing. All the information we can able to identify with the help of the Bloch-Beer. So, like, till now we have seen about the basics of, till now we have seen about the basics of quantum computing and then quantum circuits. So on the next topic, like, we will see, like, about the quantum machine learning and then federated learning. So I will just take a break of 5 minutes, and, like, if you have any questions, maybe you can ask now. Okay. So maybe, like, you can have your questions. So I will take 5 minutes break, and then I will be starting the next topic. Welcome back. So next we are going to see about machine learning and then federated learning basics. So as we know, machine learning is a branch of it's a branch of artificial intelligence that enable the system to learn from data. So like here, like what ML algorithm will do is it will identify the patterns. Basically, like what we'll do is we'll train the data. So once we are training the data, in the training phase, we will generate one hypothesis. With the help of hypothesis, what we will do is we will verify with the we will verify with the we will validate and verify the trained data, and we will see like whether it is predicting correctly or not. So after validating and verification, what we'll do for new data whether it is predicting correctly or not. So that is how we will perform the machine learning, right? So there are three different types of machine learning are there. One is a supervised learning, and the next one is unsupervised, and then the third one is a reinforcement learning. So basically, here, in the supervised learning, we are performing the learning operation with the help of the labeled data. Labeled data in the sense we will have a data, we will have all the features we will have it. From the features we will train the model. So once we train the model, we will validate and verify it. So after that, we will predict for the new cases. So that's how supervised learning will work. In case of unsupervised learning, what we will do is we will work on the unlabeled data. So we doesn't have any labeled data. So we will have unlabeled data as that. From the unlabeled data, what we are trying to find, we will trying to find that any pattern or anything we can able to any classification we can able to do or not. With that we can perform with the help of the unsupervised learning. And in case of reinforcement learning, here we will have so we will interact with the environments. So what will here we'll have interact with the help of environments. So the environment in the sense mm, so let us take a chess as an example. So what we will do is each coin there are 16 pawns will be there, and two kings each coin will have their own behavior. So the pawn can move at first move can move to two steps and also if any opposite pawn or that it can attack the pawn and it can win the pawn. So similarly each one is having its own behavior. So in case of reinforcement learning, what we'll do is that all the behaviors of different different coins will be represented in the form of states. We will represent in the form of states. And if you're performing some action in the sense you are moving from one position to another position, okay, that movement resultant in a positive way or negative way, that we can identify with the help of the reward and penalty system. That we can able to identify with the help of the reward and penalty system. So with the help of this thing, you can able to figure you can able to figure out what will set of sequence of moves whether we will win or lose the day. We can able to train with the help of the reinforcement learning. So basically so what we will do is uh, from the chess masters are playing, right? From that we will get the what are the sequence of steps they are following. With the help of all the information we will train the with the help of those data sets we will train the system. And so once you train for all the all the data sets, so if you have if human is playing, you can automatically play a move. So usually the data flow will be initially the data will be there. So we will pick the data and we will train them. We will train the model. So basically we will train the model. This is we will create some hypothesis. We will create some hypothesis. With the help of the hypothesis, we will predict the model. So these are differences In supervised learning, we will use a labeled data. In unsupervised learning, we will use a unlabeled data. Here we will use here we will learn with the help of the reward and penalties. Here input output mapping will be there in case of supervised learning. In case of unsupervised learning, like we will find the hidden patterns, and in case of reinforcement learning, like agent interact with the environment. So the examples are here, like the spam detection and then the image classification. In case of unsupervised learning, the examples are cluster segmentation and market analysis. The example for reinforcement learning, as I already told, like chess is another example, and the robotics, like the movement of the robots. So the movements will be trained with the help of the states and the environment, and with the help of the reward and penalty system. So based upon that, like the robot can automatically move from source to the destination, or it can choose its own path. It can select its own path. The next we will see about federated learning. So the federated learning concept is a decentralized machine learning approach. Like here, what we are doing, we are collecting the data in the central server and training on locally on user devices. So we are collecting data on the central server, and also we are training occurs locally on each user devices. So here only model update or parameters are shared with the global servers, so not the raw data. What we are doing, we are only sharing the metadata. We are sharing the metadata, or else we can share the model updates or only parameters. So we are not sharing the raw data, so that improving the privacy and security with the help of the federated learning. So here how the training will happen, like the training will happen both locally also, and also in the server also training is happening. So the server training is happening based upon the model update from every clients, or every local or from the like a different clients. But local training is happening individually based upon the data which you get from the local devices, or from the edge, like nearby data, or edge data, or sensor data. So this is like working of federated learning. So here, like what we are doing is a global model is initiated at the central server. So the servers send the model to the multiple clients. So initially, like so the model will be distributed by the server to all the clients. So now each and every client will have a model to run. So there you will get a data. So each clients get a data from the local data. So the model will be trained based upon the data which you are getting for each clients. So local data, that all the local models will be sent back to the server for the further update, or further update, or once it is aggregated, once it's aggregated from all the clients, what it will do is, like, it will model will be updated. Those updated model will be sent again to the each clients. This process will repeat until unless the model is stable. So till the time, like even like a client will learn from the local data, and server will learn from all the client local, like all the client model updates, and it will be updated in the it will be updated in the server either by aggregation, and whatever the aggregations happen, if there is no change between the client between the local model update and then client server model update, if there is no change, then the algorithm will stop. So the advantages are the privacy preservation, and then reduce communication overhead, and support for distributed edge intelligence. So next we will see about the quantum machine learning, and then federated learning. why we need a quantum machine learning? So we can able to solve with the help of machine learning approaches, right? Like why we need a quantum machine learning? So as I already told, like here we have a parallelism will be there. So for certain data types, we can able to compute much faster than the machine learning approaches. That means like when and all it will be is like for high dimensional data, it will be very much helpful. And for large scale optimization, it will be very much helpful. And for computational complexity, that means high computational complexity. As I told, like RSA algorithm and all, like it takes like so much time to compute the encrypted value, to decrypt the encrypted value in the classical system. It takes so much time, but in case of quantum computing, it will be it will be like the RSL algorithm will be compromised in much less time. And also like modern application generating a massive data sets. So let us take an example like IoT devices and all. Like it will have like tons and tons of data will be produced from each and every devices, and all the data is also heterogeneous types. It is not the same data type. It will be a heterogeneous data type will be there. So getting data from all the thing and analyzing the data, it is a uh, like a tough task. So with the help of content computing, we can able to perform. And similarly for healthcare system, so our healthcare system, like there we will have sensitive data will be there. So all the sensitive data will be like if you are transferring with the help of a classical encryption method, like here it will be compromised. So to overcome that one, like we are using for encryption algorithm for the healthcare system, and similarly for financial platforms and the smart networks, we are using a quantum machine learning. So what are the advantages are like it is doing like parallelism and like a faster search and optimization will be there, and it will be like efficient feature representation, and it will be having improved computational speed. So the quantum machine learning combines both quantum computing concept and then machine learning complex to solve the complex problem more efficiently. So quantum machine learning it's a combination of both quantum computing plus machine learning. So what we are doing is like here we are using the basic concepts. So here we are using the quantum computing basic concepts such as superposition, entanglement, and quantum parallelism. So with the help of those things, like we are improving the efficiency of the learning and then optimization task. So like in the quantum machine learning, what we are doing, we are combining the quantum circuit with the classical machine learning techniques. So like the thing is like in case of like classical machine learning, like we will have only training data will be there, and that will be like a trained with the help of the data, with the help of labeled or unlabeled data, and it will be we will predict the output. But in case of QML, what we are doing, like we will create a quantum circuit, and we will encode the data. We will encode the classical data into quantum data. So after encoded, like it will be sending to the that means like quantum machine learning algorithm, it will be sent. So there it will process the remaining like the principle wise there will be no much difference, but the way we are doing, the way we are approaching, it's slightly matters, slightly change in case of quantum computing. In case of classical machine learning, like we will simply send the normal like classical data in the sense like normal data only. But in case of quantum computing, even like we can send directly the classical data with the help of quantum machine learning, that it can perform much lesser. So to improve the efficiency, like what we are doing, we are performing like a encoding in the sense we are just converting the classical data into quantum data, and then we are sending to the quantum machine learning. So it can work in any ways. Like either you can use a quantum circuit for classical data. Also, you can use it, or you can use a quantum data with quantum machine learning approach. Also, you can use it. Like it will work in for all the cases. But the thing is, if you're using like a quantum encoded data in the quantum machine learning approach, then there will be more chances are there it will be solved faster. So application which I have already seen, we will see an example for different types of quantum machine learning. So like quantum machine learning techniques are broadly classified into three categories. Like one is a quantum enhanced machine learning, and then the hybrid quantum classical learning, and then fully quantum machine learning. So so in the case of the quantum enhanced machine learning is like classical machine learning accelerated with the help of the quantum computation. Here we will improve the optimization and search efficiency. In case of hybrid quantum classical learning, what we are doing, we are combining quantum circuit with classical neural network. And here we have like in the NISC era, like devices and all, mostly this approach we are using. And the fully quantum machine learning, we are using the entire learning process run on the quantum hardware only. So here you use the quantum data and also the quantum algorithm. So as I already told, right, so in all the cases, it will work. But the thing here is in the fully quantum machine learning, why we are using fully quantum data and we are running the quantum algorithms, that we will get a improved efficiency. They will get improved efficiency compared to the previous cases. So classical data with classical machine learning is a traditional approach. Classical data with quantum machine learning is a classical data with the quantum algorithm, that is like a hybrid one. And similarly, normal data with quantum algorithms, there is also hybrid one. And so both quantum and quantum algorithms, that is a fully quantum machine learning. So totally 4 different types are there. One is a normal one is a normal classical approach, and all the combinations, the quantum data with classical machine learning, classical data with quantum machine learning, and quantum data with quantum machine learning algorithms. So we will see one example of quantum support vector mission. So it is a like quantum version of the classical support vector mission. So here we have the feature mapping and kernel. So what quantum SVM uses is quantum computing to improve feature mapping and kernel computation, and then classification efficiency. It will improve with the help of quantum SVM. So here we have classical data is encoded into the quantum state using the quantum feature map. So after we have encoded the data in the quantum, so after the classical data is encoded to a quantum data, so what we are doing, we are quantum circuits compute the similarity between the data point in the high dimensional Hilbert space, and from this we are performing the complex classification problems. So these are the advantages. You will have a faster kernel evaluation, and it will be efficient handling of complex data set. And also we will use a variation quantum circuit for parameterizing the quantum circuit in the quantum machine learning. So there will be two different various quantum circuits are there. One is a quantum computation and another one is a classical optimization. So where and all it is used is like we are using the quantum classification and then quantum neural network and then optimization problem. So what we'll do is here we will have a phase will be there. The phase will be sent to the quantum circuit. That will perform the measurement. From there, we will find the loss functions. With the help of the loss function, we will we will try to find the optimized value. So this is an architecture for quantum machine learning architecture. So if you take the first one is like a data input, like here we have a classical data, like the data can be of a raw input data, images or signals. So first what we need to do is like we have to encode the data in the form of quantum states. So once we encode it, then we will send it to the parameterized quantum circuit. So now that means like a quantum data we are sending to the quantum model, quantum like a federated learning quantum machine learning model. So what we are doing is like here it is like what we got is the quantum data. For that, like we are performing the uh, training. So and then we are predicting the output. So and then we are predicting the output. So and then finally just checking is there any error noise or there. Is there any error like error noise or the loss ratio is like how much the loss ratio is there. We are sending the update with the help of the feedback loop. So the quantum model it will be updating that one like basically like what we are trying to do is we are reducing the error or loss. So these are the applications like we have already seen. So some of the applications are like drug discovery, financial predictions, and image classification and optimization problem and cybersecurity and IoT and edge intelligence. So similarly, QML is used in the IoT and edge computing also. So intelligent edge analytics we are using, and for resource optimization we can use it. And similarly, for smart healthcare system, we can use like federated quantum learning. We can use it, and 6G intelligent networks like mobile networks, like 6G intelligent vehicular networks. We can use it. So next we will see about like quantum federated learning. So by the time like we are aware of like how we can perform like a normal. So how quantum machine learning is different from normal machine learning is based upon like either you can change the like quantum algorithm, you can change it, or else like you can change the classical data into encode into quantum state data. From there like you can send the quantum data to the quantum algorithms or quantum federated learning. So those combination only, like here we are performing like quantum computing first, federated learning. So what we are doing is like as I already told, like a quantum federated learning will enable multiple distributed clients to collaboratively train the quantum machine learning models without sharing the data. So that means like in normal cases where the whatever the model trained, that metadata will be like model data trained data will be like or else the model update will be send it to the server. Here like before that like we have to whatever the data we are getting, we have to quantum that we have to make that the quantum state data. So once we make a quantum state data, from the quantum state data we will train the local clients. So once we train the local clients, the model is generated from the local data that we will send it to the server. So only quantum model parameters or updates are shared with the central server. So advantage is like it is the same only. Like the thing is like it will be um, the privacy preserving learning will be there, and distributed intelligence will be there, and quantum enhanced optimization. So because of the quantum, we will improve the performance little bit. So why? Because like we are modeling, we are encoding the data into the quantum state data, and then we are sending to the like a quantum algorithm, local quantum algorithm model in the local state. So after sending to that, like it will be trained on that like the model. Yeah. So that means like only the quantum model parameters or updates are shared with the central server. So this way, like we are doing the privacy preserving learning and then distributed intelligence and then quantum enhanced optimization. So the same thing, like the classical data we have encoded into the quantum data and then we have send it. Mistake is there. Okay, this is so. So this is like limitations of quantum machine learning. Like what are these are the certain limitations are there. So it is limited to the quantum hardware. Current quantum computers have limited number of qubits, and it will have low computational stability. And the noise and decoherence, like quantum states are highly sensitive. Like even the environment disturbance causes the computational error. So as I told, like even if you are measuring for the measurement purpose, like if you are taking like a qubit information, so it will lose its original state. It will lose its original state, and also error correction challenges will be there. Like here, so once it is get disturbed, like how we are going to reform to the original state, it is again a one challenges are there. Like still like research is going on the error correction challenge in case of quantum state, but not at complete level. So the next one is the data encoding complexity. So here, like we have to every time what we are doing, like we are converting the classical data into quantum states. That is little bit computationally expensive. So once it is done, like to process that one, it will be much more faster. So, but the thing is, like we have to convert the classical data into quantum data. That is a overhead. Overhead is there. And similarly, there is a scalability issues are there. And like large scale QML are difficult to implement on the present day quantum devices. So because like till now like quantum is an emerging stage. Like till now like around 40, 22 qubit states only they have built it, like not more than that. So that is one disadvantages. Like so we can't able to like, but with the help of the simulation model we can able to run that one. So lack of mature algorithms. So only for few like we have quantum algorithms are there. Like not for all the algorithms. Like still like people are working on that like rigorously to create a more mature algorithms for the case of quantum machine learning. And this is the finally the last is like what we have learned is like we have learned about like what is quantum computing and how we will create a circuits. Okay, how we'll create a circuits and what is a quantum machine learning like so how we'll implement the federated learning in the quantum we have seen. Okay, so the quantum machine learning integrate like as I told like quantum computing with artificial intelligence. So these are the applications where we are using, and similarly, like we have like federated learning is just enhance the privacy preserving distributed AI system. And in case of quantum federated learning, combine both secure collaborative learning with quantum intelligence. So basically, for complex problems, we will use a like like complex problem we will go for the quantum machine learning, and these are like some of the future directions of research. Like here like will develop the development of fault tolerant quantum computers. Like in the hardware level we can like fault tolerant quantum computers we can work on that, or scalable quantum machine learning architecture. Like till now this architecture is more dependent on the data, and also it is more dependent on like encoding the data. It has become a overhead. So how we can resolve this one like and once it is there like we doesn't have like a machine learning algorithm for all like all classical machine learning algorithms. We haven't we haven't seen like a quantum we haven't developed the quantum algorithm. Still, there is a research gap is there that we can work on. And quantum federation for secure distributed AI and hybrid quantum classical AI systems are there. So quantum enabled IoT and edge intelligence that we can focus on. Similarly, with the help of federated learning also, we can be able to solve the problem. And noise reductions and quantum error correction is a is a like a research area still working on that. Like there is no proper error correction or proper noise reduction in case of quantum states. Like in the qubits, like once the data changes its form, we can't able to recover to its original form. The error correction techniques are not fully mature. Like there are also certain drawbacks of that. And efficient encoding data encoding methods still people are working on. So future like this is a future vision, like a future intelligence system are expected to combine both quantum computing, AI, and edge intelligence to make a secure distributing learning. And you have any questions?
Yes, sir. Yes, sir. We will open the floor for participant side queries, sir. Yes. Dear participants, if you have any questions or clarification, please unmute yourself and raise your queries. Sarah is here with us to clarify our doubts. Yes, anyone having any doubts? Okay, sir. I deliver my vote of thanks, sir. On behalf of the organizing team, I would like to express sincere gratitude to Dr. R. Dinesh for delivering such an insightful and enriching session on classical federated learning to quantum paradigms, core concepts and limitations. The presentation provided us with a clear understanding of the evolving concepts in federated learning and quantum paradigms. The knowledge, ideas, and insights shared during this session were truly valuable and informative for all the participants. Thank you, sir, for taking your valuable time to be part of this faculty development program and for sharing your expertise with us. We sincerely appreciate your effort and contribution. Once again, thank you so much, sir. Yes, sir.
Thank you, ma'am, and thank you. I want to thank for the management for giving me
Yes.
this opportunity,
Thank you, sir.
and thank you for all the audience.
Yes, sir.
And thank you, ma'am. Thank you, ma'am.
Thank you, sir. Thank you so much, sir. Yes, sir. Dear participants, with this, today's program concludes. Thank you for your valuable participation and support. I kindly request everyone to rejoin tomorrow using the same meeting link by 8:30 a.m. as the session will commence promptly at 9 a.m. And also, I kindly request all the participants to submit the feedback form without fail. Please ensure that you should maintain at least 80% of attendance, then only you can eligible to receive the certificate. Please, once you submitted your feedback form, you may kindly leave the meeting. Dear participants, you need to submit your feedback form. Already we have posted that feedback form link on chat box. You need to submit it. Once you have submitted your feedback form then you may kindly leave the meeting. Thank you so much.